A very good morning to all of you. First and foremost, if the audio and video are clear, please give me a thumbs up. Okay, great to see. Great to see. Let's begin with our classes. Before we begin, first of all, a very, very congratulations to all of you on the successful launch of the L1 mission. And let's hope that it reaches its orbit also successfully. I think it's going to take approximately, 125, 126 days for it to reach there, and then it will start operating from the L1 orbit. All right. So let's begin. So today's class, we are going to first continue from where we left in the last class, that is about nuclear energy, where we are going to discuss first about nuclear fusion. And after that, there are some of the additional smaller areas that we have to discuss here. Now, after that, once we are done with this chapter, we'll start with the next chapter. The next chapter is biotechnology. So we'll be able to complete one part of biotechnology in today's class. So this is what is in store for today. So let's begin. The first topic for us here is nuclear fusion. Now, in the last class, we had discussed about nuclear fission. And in case of nuclear fission, we discussed about how uranium is used for nuclear fission, where uranium will split into two parts while releasing a lot of energy, right? In this scenario, the term is fusion. What is the meaning of fusion? Fusion means to fuse means to join something. All right. So when you join two pieces together, you say that you are fusing things together. Similarly, when we say that it is nuclear fusion, means that there are two things that will combine, and while combining, they actually release a lot of energy. So what combines? What we see here is that there would be these isotopes of hydrogen that can combine together, and while they combine, they can form helium. While forming helium, they also release a lot of energy. So this is what we basically see in any given typical nuclear fusion, where two lightweight nuclear fuels are combined and they form a nucleus of a heavy element. Now, in this particular scenario, what exactly happens in case of nuclear fusion is that we see that under very special conditions, there are chances that these isotopes might combine together. Now, just remember that the kind of instability that we see in uranium or anything that is very heavy, that kind of instability is absent in hydrogen, right? Because what was the basic factor there? The basic factor was that inside the atom, you have a very small space, and this small space is called as nucleus. And inside the nucleus, you have a lot of protons. So obviously, protons will repel each other, and there will be a problem, especially if the number of protons is very high, right? So if the number is very high, so it will definitely produce some problem there. So ultimately, what happens is that it starts to break because of the instability there. Now, in this scenario, so it was like, let's say, where you are in a classroom, and in the classroom, first only morning batch students are sitting, and then I also call upon the evening batch students, and then also I call upon the weekend batch students. So everyone is sitting in a very small classroom. Suppose that instead of an online classroom, it was an offline classroom, and in this first only morning batch, and then evening batch, and then weekend batch also starts and sits. So there will be no space for everyone to sit, and then there will be a lot of instability in the classroom, and you perhaps will start to throw away the people who came from other batches, right? So those kind of scenarios will be present. So that is what is happening in nuclear fission. So just imagine that you are alone sitting in this classroom, and you are having this premium service where this is a one-on-one classroom that only you are the only student and I'm the only teacher. So then in that case, there is no instability, right? You are also stuck. You can't do anything. You have to study and you have to concentrate because you're the only one in the classroom. So there's no instability here as such. So only under very specific conditions, instability will have to be produced. And this kind of instability is produced under specific conditions of very high temperature, very high pressure, and very strong magnetic field. So if you look at the screen and the equations that you see here, this is what happens inside the sun. This is typically what happens inside the sun. Right? This is typically what happens inside the sun. Now, in this particular scenario, let's see what happens. First, you have two normal hydrogen. They fuse together and they are forming deuterium. All right, they are forming deuterium. Now, this deuterium combines with more of hydrogen to form helium-3. If you see here, this is helium-3. So now helium-3 is not really stable. This is an unstable form of helium. So this helium-3 quickly combines with more of itself to ultimately form helium-4. So this is the helium that is stable. This is the helium that is stable. So if you look at the entire equation, what we are seeing is that hydrogen is getting converted into helium. Hydrogen is getting converted into helium while releasing a lot of particles, which correspond to the kind of energy that is released in such equations. Now, overall, what we see is that in this particular scenario, for a nuclear fusion reaction to occur, these two particles, they have to be brought very close to one another. Right? They have to be brought very close to one another, and then only it is possible that we'll be able to activate them. So that's why it is necessary to bring two nuclei so close that the nuclear forces between them become active and make them to stick together. So now in this particular scenario, what we see is that there are, as I told you, I'm just writing it here. There are very special conditions that are required for something like this to happen, and these special conditions could be very high temperature. Or let me write extremely high temperature. Extremely high temperature, extremely high pressure, extremely strong magnetic field. Right? So these are the certain conditions under which something like this is made to be possible. Now, in the sun or inside any other star, this is something that happens naturally. Correct? It happens naturally there. But we also want to tap into this energy. We also know that this is a form of energy that can be extremely useful to us. It's a form of energy that can solve all our energy problems if we are able to master it. So that's why we have been trying to master it, and we have been trying various different experiments in various different ways, so that we ultimately get to a position where we can use nuclear fusion to generate electricity. So there are certain approaches that have been used. These are called as confinement approaches. There are two important confinement approaches that are used so that we can make nuclear fusion possible. What are these? The first one is magnetic confinement. First one is called as magnetic confinement. The other one is called as inertial confinement. Now, in case of magnetic confinement, what we basically see is that the term is magnetic. So what we do is that we use very strong magnetic field, and under these conditions of very strong magnetic field, the charged particles, also called as plasma, these plasma would be confined. All right, the plasma would be confined within the magnetic field, and the plasma will be made to stick together. And if the plasma sticks together, we release energy from here. So this is basically what we do. That we use very strong magnetic field to confine the plasma, to create the conditions needed for fusion energy by using electrical conductivity of the plasma to contain it within the magnetic field. Now, this magnetic field that we have here is in a toroidal shape. We have toroidal shaped magnetic coil. You know what toroidal shape is like? Toroidal shape is like, I mean, if you have eaten donut, so that donut is a toroidal shape, or even let's say a tire, shape of a tire. So that can be called as a toroidal shape. So now, so that's why that is the shape of the coil. All right. So in that coil that you have, so just imagine the shape of a donut, or just imagine the shape of a tire where you have a broad ring-like structure. So that is called as the toroidal shape. All right. So you have a toroidal shaped magnetic coil, and the plasma is basically confined inside it. All right. So there is a very important experiment that has been going on, and that is ITER, International Thermonuclear Experimental Reactor, where there is this kind of a magnetic coil which has been named as tokamak. Sometimes you will see this in the news. The name tokamak will be in the news sometimes. So that's why we see that in this particular scenario, this is what we have been trying. All right. The second one is called as the inertial confinement. So inertial confinement, what we do is that we use powerful laser or ion beams to compress a pellet of fusion. So this time, instead of using a magnetic field, we are using lasers. All right, we are using lasers, and with the help of lasers, we are trying to drive the plasma near one another so that fusion can be made possible. So this, in this particular scenario, the inertial confinement fusion, again, this is one way in which we have been trying. And in the last 1 year, this particular kind of confinement, that is called as the inertial confinement, has been in the news twice. Once last year in the month of December, and then again this now not this month, last month, that is in the month of August. So in the month of August also, this was in the news. So these two news articles, the news clippings that you see here, these basically what we see is that this is something that has been achieved with the help of inertial confinement. Now, so these two basically are related to inertial confinement. Now, what exactly this news is related to, let me just tell you about this. So why? So first, look at the first article. Why fusion could be a clean energy breakthrough, and the second one is scientists repeat fusion power breakthrough for the second time. So both these articles, they are basically talking about some kind of breakthrough. They're talking about some kind of breakthrough, right? In both these articles, as you see, some kind of breakthrough is what we are talking about. So this breakthrough basically is something related to the laser confinement or the inertial confinement. What we have been able to do for the first time, why we are calling this as a breakthrough, what have we been able to do for the first time is that we were able to produce more energy than we consumed. So you think that it is so trivial that we are saying that we produce more energy than we consume. This has been the biggest problem until now for nuclear fusion, because in nuclear fusion, it's not that experimentally we have not succeeded. We have succeeded. We have been able to produce fusion-based energy, but the problem is we have used more energy to produce that energy. Now, ultimately, if you want something to be used on a daily basis, if you want something to be used commercially, if you want that you are driving electricity into homes with the help of nuclear fusion, then in that case, if you are using more energy than you actually produce, then it makes no sense. It doesn't mean anything if you are using 100 joules of energy and producing 50 joules of energy. It should be opposite of that. That you use 50 joules of energy and you produce 100 joules of energy, right? So that's not happening. That hasn't been happening in nuclear fusion, and we have been trying for a very, very long time. So ultimately, December 2022, we finally were able to get success here. Right? We were able to get success, and this success was related to nuclear fusion in a manner that more energy for the first time was generated than what we consumed. So, and it was not a huge amount of energy. It's not that they produced huge amount of energy. It was only, as the scientists had put in, that it was only enough to boil some kettles of water. That's it. Right? So, but still, we are talking about this. We are calling it as a breakthrough mainly because of the fact that this is for the first time that we have been able to do that. And just know a few things, that it is related to inertial confinement, where with the help of lasers, we have been able to produce more energy than we consumed in the operations for the first time. So that's why this becomes a very, very crucial perspective, because until now, this has been the thing that, I mean, when last year when this breakthrough happened, the scientists said that now fusion is only 20 years away, and this fusion being 20 years away is something that we have been hearing for a very long time. And even in the 1980s, we were saying that fusion is something that's just 20 years away, and in 2023 also we are saying that now it is almost 20 years away. So this is something that I mean, obviously it's not a very easy technology to master. It has been one of the most complex technologies to handle because of the conditions that are required. Only there are certain experiments that have worked. ITR experimentally has worked. China made something called as artificial sun that also uses magnetic confinement. So that's another similar experiment. And the third one, the Lawrence lab that we have in US, which has been using inertial confinement. So these are certain successes that we have. But again, breakthrough was first. With the help of ITR or with the help of the artificial sun that China has, we haven't been able to reach the kind of level that Lawrence Lab last year was able to. So that is why we see that we still are looking forward to it. We still are looking ahead in the next 20 years to find out whether or not something happens. Because see, even when we say that it is a breakthrough, the breakthrough only signifies that okay, we were able to produce a little more energy than we consumed. All right, we consumed 100 joules of energy, so we produce 120 joules of energy. So 20 extra joules of energy for the first time we were able to generate. That's it. Correct. Until the time we are able to produce a significantly more amount of energy than we are consuming, we wouldn't be able to call it useful. All right, in the basic meaning of the term, we wouldn't be able to call it as useful until the time we are able to get a proper success out of it. Correct. So that has been what's missing here. We haven't been able to do that, and it's not that, I mean, with the breakthrough you quickly be able to get that energy. Even whenever any new invention, any new discovery happens, you'll see that after that it takes some time before it is actually commercially available. The first flight, all right, the first flight by Wright brothers happened in, I think, somewhere around 1905, if I'm not wrong, 1903, 1905. And then it took almost 45 years after that until the time the first domestic commercial aircraft could fly. So it took time, right? It took time from the first time the invention happened to the time that the commercial flight could actually take. So take off. So that's why just remember that it's not that with this breakthrough all of a sudden nuclear fusion will become a possibility or it will become a reality, if it will become useful in the actual meaning of the term. But maybe this is where we begin. Maybe this is where we understand what needs to be done and we start to replicate it in a manner that we are able to create a big difference between the energy that we consume versus the energy that we generate. So we still have to wait. We still have to wait and see whether we are able to get the success that we need. Now, as we discussed, there is International Thermonuclear Experimental Reactor or ITER, which also has been working, and this basically has been working with magnetic confinement. This is an experiment that has been working with magnetic confinement, and that's why we are saying that it's a large-scale scientific experiment to demonstrate that it is possible to produce commercial energy from fusion. Now, when this international thermonuclear experimental reactor began, there were three important participants. We had the former Soviet Union, USA, and European Union, and Japan. These were the prominent members, and then three extra members also joined. These were India, China, and South Korea. India, China, and South Korea also later became a part of ITER, and India has been a very crucial part of ITER today. A lot of investment has been going from India. A lot of experiments have been conducted with the help of India. Some of the very crucial parts that you have in the ITER that also has been made in India, that has been made by India. So that's why we know that India also has been a significant contributor to this ITER. Now, why nuclear fusion? Right, what are the advantages that we have with nuclear fusion? So some of these things are easily explainable and these are easy to understand for you, but there are certain points which are very crucial. So first, for example, we have abundant amount of energy. We can produce some abundant amount of energy, and that's not going to be a big. Once we are able to master nuclear fusion, then energy concerns that we have today will go forever. We'll not really have those energy concerns anymore once we are able to understand how to use this energy commercially. So overall, that's why we'll see that something like this is in store in the future, where we get enough amount of energy. Then it is sustainable, meaning that we can use it for a very long time. We'll be able to use it for a very long time, and that's why we are calling it as sustainable. Then no carbon dioxide, because the reaction is completely different. It's a fusion reaction. It's not a chemical reaction. There is no carbon associated with it. The energy that we are getting is from hydrogen and helium. So that's why there is no carbon dioxide. Then no long-lived radioactive waste. And this is a very, very crucial point where we see that it becomes better than nuclear fission. Because in case of nuclear fission, we understand that the nuclear waste that we produce, it can last for a very, very long time. Right? It can last for a very, very long time. So it can become a big challenge for us to get rid of that waste. So ultimately, what we see is that it can last for more than, okay, so let's say if I ask you, for example, that when we say long-lived radioactive waste, so we discussed that uranium is used, right? Something like uranium is used, and as a byproduct, when you use uranium in nuclear fission, you get plutonium. As a byproduct, plutonium is produced. So plutonium, in a manner, can also become a radioactive waste for us. So if I ask you a question, do you know how much time does plutonium take to reduce to half of its mass? Let's say if you have 100 grams of waste, plutonium-based waste, how much time does it take to get to 50 grams of the leftover? Any guesses? 200 to 300 years, 87 years, 1000 years, some thousand, 36,000. Yes, Yashpal, your answer is correct. So that's why just know this, that it takes almost 24,000 years. That's why we are seeing long-lived radioactive waste. 24,000 years. So that's why what happens is that once a kind of leakage happens, it can remain in the atmosphere for a very long time. It may not be very harmful after a while. After maybe 50, 60, 70 odd years, it might not be very harmful, but it will remain in the atmosphere. It will remain there for a very long time. For example, I'm very sure that you've all heard of the Chernobyl accident. The Chernobyl accident that happened in Ukraine. At that point of time, it was a part of USSR. Now it is a part of Ukraine. So this Chernobyl accident, what happened in that was there was a nuclear leakage that happened from the nuclear reactor, and through that leakage, the radioactive waste that got out. Because of those radioactive waste, these are areas which are still not habitable. There's still areas where people are not allowed to live because it will be very, very harmful for the health of anyone who resides there. So almost 35, almost let's say approaching 40 years later, we still are facing that problem, and even for the next 20 odd years, we perhaps will be in a very similar situation. So that's why when it comes to nuclear fission, we see that this is a big challenge, that there are a lot of long-lived radioactive wastes. All right. So this is also one major point to be considered, that there are long-lived radioactive wastes that we have in case of nuclear fission, which again in case of nuclear fusion is never a challenge. All right. In case of nuclear fusion, it is never a challenge because this is something that does not create any kind of radioactive pollution. Just give me one moment, please. Yeah, all clear? Voice and audio both are clear? Yeah. So we know that long-lived radioactive wastes are a big challenge. Whereas when it comes to nuclear fusion, in case of nuclear fusion, the waste that is generated is tritium water. Right? The waste that we generate is tritium water, which is basically denoted by T2O. And now this tritium water also is very unstable, and what happens is that it very quickly converts into normal water. So what we see is that it will quickly convert into H2O or the normal water. So that's why there is no radioactive waste, because the tritium water, because of tritium, is not very stable, and it quickly converts into normal water. So that's why it does not create any kind of waste, the kind of waste that is generated in nuclear fission. Then limited risk of proliferation. Now when we say proliferation, the meaning is weaponization. Now if you remember, we discussed that when it comes to nuclear fission, in case of nuclear fission, we need to ensure that the enrichment that is done, the enrichment of uranium should not be beyond 3 to 5%. Correct? The enrichment is 3 to 5%. And if you go beyond 5%, if you start going beyond 5%, then it means that you're trying to reach towards a level where you can create atom bomb. So from the same process where you're creating nuclear fission based electricity, from the same process, you can even produce atom bomb, something that we'll discuss a little later today. So same process. So the risk of proliferation is very high. Risk of weaponization is very high. Plutonium that is produced as a byproduct of nuclear fission, plutonium can very easily be weaponized. Plutonium can be used as a nuclear weapon very easily. So that's why This is basically what happens in this particular scenario, and that kind of risk in nuclear fusion process is pretty limited. So that's, but remember, limited. We are not saying no risk of proliferation. We are saying limited risk of proliferation. Doing that from the same process is difficult. That, for example, if you think of a fusion bomb or hydrogen bomb, the method that is used to make hydrogen bomb is completely different. It's completely different compared to how we use nuclear fusion for electricity generation. So that's why even if somebody is making a fusion based weapon, they would be using a completely different facility. They would be using completely different process, and then they'll be able to make it. They cannot make it through their nuclear fusion power plants. So that's the advantage that we have, and no risk of meltdown. The kind of meltdown problems that we see with nuclear fission, that kind of an issue also does not exist with nuclear fusion. The kinds of accidents, for example, that we have seen in Fukushima, for example, in Japan. So those kind of problems will not happen in case of nuclear fusion. So that's why nuclear fusion, compared to other sources of energy, it definitely has an advantage. But even compared to nuclear fission, we see that it has a lot of advantages. And even the cost factor, that once we are able to scale it up, once we are able to commercialize it, after that, the cost factor cost will be very, very low. It will be very cheap source of energy, and while being abundant, while being sustainable, while being pollution free, while being accident free. So that's why nuclear fusion. That's why we, even though it has been so complex to use it, we have been trying with a very limited success for a very, very long time. Yet we have not given up, because we know that the day we are able to crack it, the day we are able to use nuclear fusion as a source of energy, will be the day where this whole chapter that we have been studying for 3 days will be reduced to one small chapter of nuclear fusion. Because then no coal, no petroleum, even solar energy, wind energy, nobody will need, only nuclear fusion, right? So that's why we see that there are so many advantages that nuclear fusion has. Look at this question. This was asked in your 2016 paper. Please read the question and then I'll launch the poll for you. I'm launching the poll. It's an easy question. Please look at the keywords. You'll definitely get the answer easily. Okay, so 66% of you have marked D, which is the correct answer. A lot of you have marked, surprisingly, a lot of you have marked C. Let me give you the answer to this question. India is an important member of the International Thermonuclear Experimental Reactor. If this experiment succeeds, what is the immediate advantage for India? First, it can use thorium in place of uranium. We are talking about International Thermonuclear Experimental Reactor, ITER. What did we discuss about ITER? That we are using magnetic field, right? Magnetic confinement there. So magnetic confinement for hydrogen, the fusion of hydrogen into helium. So there is no thorium, there is no uranium. So that's why A does not make any sense. B is it can attain global role in satellite navigation. So it's nothing to do with satellite navigation. It can drastically improve the efficiency of its fission reactors. Is ITER related to fission at all? No, it is related to nuclear fusion. We have been talking about nuclear fusion. It has nothing to do with nuclear fission, correct? So that's why this is wrong. And it can build fusion reactors for power generation. This is what we are trying to do. We are trying to see how can we scale up using nuclear fusion for energy. Now to talk about nuclear reactors. So until now, we now know the concept of what is nuclear fission and what is nuclear fusion. Nuclear fusion is something that is 20 years away, that in the next 20 years we'll have nuclear fusion. But right now the energy that we produce, the energy is produced with the help of nuclear fission. And with this nuclear fission, this is a typical nuclear reactor that is used to tap the energy of nuclear fission. So how exactly it works, let's try to understand. So in this, if you look at this part, what you understand is that there are two parts of the reactor, this part and this part. The first part is the part where nuclear fission is going on. So here, as you can see, you have the core, right? You have the core, and this core is where all the nuclear reactions occur. This core is where all the nuclear reactions occur. So this core will have uranium. The core will have uranium, and this is where nuclear fusion would occur. Then you have control rods. Control rods are specifically made of certain metals so that they can absorb extra neutrons from the core. So what we discussed, remember that the reaction can go uncontrolled if you have extra neutrons, right? This is what we had discussed in the last class, that you have extra neutrons. If you have more neutrons than what is required, then the reaction can go uncontrolled. So to control the number of these neutrons, we have control rods, right? Then that's the role of a control rod, that if there are extra neutrons, we will insert the control rod inside the reactor. It will absorb the extra neutrons, and then this control rod will be pulled back. So it is made of metals like boron, cadmium, etc. Then the reflector basically is nothing but the boundary, the casing of this nuclear reactor, so that none of the nuclear particles go out, none of these radioactive particles or high energy particles like gamma radiations or even neutrons, for example. To ensure that they do not go out of the reactor, we have this reflector or the boundary or the wall that will prevent that from happening. Then apart from that, as you can see, you have something called as a coolant. Now this coolant basically is a kind of material. The coolant is a kind of material that is required so that we can transfer this energy. We can transfer the energy, or whatever energy is produced, that can be transferred towards the turbine. For that we have the coolant. For example, water can be a coolant. That water will go into the nuclear reactor core, and the nuclear reactor core would have become very hot because of the nuclear energy, and the energy is basically in the form of heat. So this heat will be absorbed by water, and this water will be carried to the secondary side where basically coolant will be used. This water, which might have converted into steam by now, the steam will be used to rotate the turbine, and hence electricity generation will happen there. Apart from all these things, there is one more part inside which is called as a moderator. Now moderator may or may not be present in a reactor. In some of the reactors it is present, in some of the reactors it is not required. So moderator basically is required whenever we need to slow down the speed of neutrons. Many of the reactors, or most of the reactors, I would say, most of the reactors that we use, they need neutrons to travel at a certain speed. So what happens is that naturally neutrons are faster than that. Naturally neutrons are faster. So to slow down the fast moving neutrons, to control the speed of the neutrons, we have moderators. All right. This is how we have the moderators. This is where we see the use of moderators. That moderators basically will be formed. Moderators will be used so that we can slow down the speed of fast moving neutrons. So to control the number of neutrons, we have control rods. To control the speed of neutrons, we have moderators. So that's why moderators and control rods, they play a very, very important role in ensuring that the reaction takes place at the required rate and we do not go beyond that, and the reaction is controlled and sustainable so that there is no safety issues as such in this reactor. So to summarize all these points, first we have the reactor vessel. So reactor vessel is the entire structure that contains all the reactor parts, so holds all the other reactor parts. Then after that, we see that there are steel walls or even sometimes concrete walls. So steel walls or concrete walls will be used, which are at least 15 centimeter thick. Then we have the core. So core of the reactor, as we discussed, this is where the nuclear reaction occurs. So this is where the fission would occur. And then after that, we see that we have the control rods. So for the control rods, we discussed that these are metal rods. Elements such as boron or cadmium can be there, and they would absorb the free neutrons, thus help control the chain reaction. All right, they will help in controlling the chain reaction by absorbing any extra neutron that might be there inside the core. And then we discussed that we have something called as a moderator. So moderator could be made of water. Sometimes carbon also is used. I mean, graphite is used, and this will basically try to slow down the neutrons which pass through it. So that's why what they do is that in this chain reaction, the reaction to occur at an optimum rate, we need slower neutrons. That is where the moderators come into the picture. And then lastly, we have the coolant. And coolant can be water or carbon dioxide or even liquid sodium is used, where we see that it conducts heat well but does not easily absorb free neutrons. Because it is because for absorbing neutrons we already have the control rods. So apart from control rods, somebody else also starts to do the same role that is given to control rod. Then what happens is that the number of neutrons that is there inside the core might start to decrease, and you might have a number which is lesser than what was required. So in such a scenario, what then happens is that the reaction would not happen sustainably and it might stop very quickly. So that is why coolant will have to be made of a material that will conduct the heat well, will be able to absorb the heat and carry it to the turbine very easily without absorbing any neutron. Alright, so these are the parts of a nuclear reactor. Now coming to the different types of nuclear reactor that we have, now in the world there are multiple different types of nuclear reactors. We are not really concerned with them. We are only concerned about the nuclear reactors that India has, the nuclear reactors that India has been using, or India has plans to use maybe in the future, even if it is not using it today. So these are the nuclear reactors that we need to discuss about, we need to be aware about. So first one here is the pressurized heavy water reactor. Now this pressurized heavy water reactor, these are the reactors which are perhaps the most common of the reactor designs in the world. Even in India, out of all the reactors that we have, out of we can say 21 reactors that we have, 18 reactors out of them are just pressurized heavy water reactors. So that's why in the India's nuclear reactor mix, the maximum number is occupied by pressurized heavy water reactor. So in case of pressurized heavy water reactor, we have enriched uranium that we use as a fuel, and the moderator and the coolant will be water, and specifically it will be heavy water. Now just understand what exactly we are doing in this particular scenario. So what we basically see is that when we are using high pressure, so just look at this, you'll get a better understanding of what's happening. So what we see is that you have the fuel elements here. You have the fuel elements here, which are made of course, they are made of uranium. Right? Uranium is the fuel that we are using here. So you have uranium, and then you have the control rods. Correct? You have uranium and you have the control rods. Now, in case of the control rods, which are made of boron and cadmium, what we basically see is that they will have their own functions that we know of. That control rods will take away any extra neutron that you might have here. Now, then there are these pressure tubes, and overall we maintain high pressure. Overall, we are trying to maintain high pressure, and then there is something called as the steam generator, which will convert water into steam, and the steam will be carried to the turbine. It will be carried to the turbine. From the turbine, the same steam will now move to a condenser. It will move to a condenser and then again be converted back into water. So now what happens is that we now again have water in its liquid state, which had converted into its gaseous state because of the heat. So what we see is that again with the help of a pump, this is a pump, with the help of a pump, we'll again be sending back water into the reactor, and in this manner, this particular cycle continues for a very long time. Now, so what happens is, just understand this, that what we are basically saying is that this is a pressurized heavy water reactor. Let's try to understand two questions. Why pressurized? Why pressurized is the first question, and second question is why heavy water? So there are two questions, and that's the basic concept here. There are two questions, that why pressurized and why heavy water. Anyone who can answer this question, you can just try this question and anyway give you the answer, no worries. Okay, Abhishek, you have given the correct answer. That's great. All right. Yeah, so a lot of you have given the correct answer. That's great. So let me just explain this for you, for the rest of you. So why pressurized? That what happens if we are keeping this entire reaction under high pressure? Under conditions of high pressure, what we see is that if the pressure is high, the boiling point of water shifts. The boiling point of water increases. All right, the boiling point of water would increase. So even at higher temperature, let's say even at 120, 150 degrees Celsius, at 150 degrees Celsius also you have liquid water. Right, at 150 degrees Celsius also you have liquid water, and it is able to absorb more heat. Right, it will be able to absorb more heat without converting into steam. So the efficiency of heat absorption will increase. A very similar approach is used in our pressure cooker also. That in the pressure cooker, what do you see? That water that you are using, because of the high pressure that is built inside the pressure cooker, that water will be able to use heat better, and that's why the food will be cooked faster, because water is not converting into steam and not just getting out of there. The water remains at its liquid state. It uses all that energy to cook the food very quickly. So So inside the pressure cooker also, we see a miniature version of what happens here. So why pressurize? Pressurize basically pressurizing this, or under high pressure conditions, we'll see that water would remain liquid while absorbing all the heat and being carried to the turbine. So that's why even if you are at a higher temperature, we see that the water used here will not convert into steam. So why pressurized? The answer is at high pressure, water doesn't convert into steam even at temperature above its boiling point. So it can absorb more heat, thus increasing the efficiency of the reactor. Okay, so this is basically what's happening here. That water, even at high pressure, if water at very high pressure, even at temperature above the boiling point, even if it is at 120 or 150 degrees Celsius, it does not change into steam, and it simply would be able to absorb a lot more heat, and it will be able to increase the efficiency of this reactor. Now, my second question: why are we using heavy water? Why are we using heavy water? Less neutron absorption, correct? To control the reaction, you can say that, yes. So first and foremost, when we say heavy water basically means deuterium water. Deuterium water, or D2O, what we denote as D2O, the isotope of hydrogen, right? So heavy hydrogen isotope. Now what's the difference? Okay, you'll also get to this answer. What is the difference between hydrogen and deuterium? What changes? What's the difference between hydrogen and deuterium? Yes, Chaitanya, you have given the correct answer. Varun correct. Anshuman correct. Abhijit right. Shubhajit right. So, correct. So a lot of you are giving the correct answer. Between hydrogen and helium, between hydrogen and deuterium, the difference is one extra neutron. Correct. Hydrogen has just one proton and one electron, whereas deuterium has one electron, one proton, and one neutron. Now, in heavy water, because you have an extra neutron, the chances that it will absorb a neutron from the core will be less. Right? It will not absorb that extra neutron. So there are higher chances that water would absorb that neutron than heavy water. So if it was normal water, there were some chances that it might absorb extra neutron because there is scope. But in case of deuterium water, that is D2O heavy water, there is no scope because it already has an extra neutron. Then it might, in that case, you might ask, then better would have been to use tritium. That why not use T2O, that is tritium water, instead of deuterium water? The reason for that is, and something that we just discussed 10 minutes back, that tritium water is highly unstable. Deuterium water is not unstable. So that's why using tritium water will be very, very difficult task for us. So that's why we don't use tritium water, and we are happy with using deuterium based water, that is heavy water. So this heavy water, what happens is that it has an extra neutron. So it minimizes the chance of absorption of neutrons in the core. Right? So that's why deuterium water is used, because deuterium water will, or the heavy water will ensure that the extra neutron does not get absorbed. So we have pressurized heavy water reactor. Now pressurized heavy water reactor is the most important design, most widely used, not only in India, but across the world. You'll see that pressurized heavy water reactor is the most widely used type of reactor. Now, apart from pressurized heavy water reactor, we also have boiling water reactor. So boiling water reactor uses enriched uranium. It also uses water. Now the basic difference between a pressurized heavy water reactor and the boiling water reactor is that the water here is the normal water. We are not pressurizing it. There is no high pressure chambers that we are creating here. We simply would put water into the reactor and let it convert into steam. So that is what basically happens. That water will simply go to the reactor. It will convert into steam. The steam will go to the turbine. From the turbine, the steam goes to the condenser. And from the condenser, because now it has again become liquid water, hence we see that through the pump, again it will be pumped back. So in this manner, this cycle will continue, and that's why a boiling water reactor. Now, the fact about boiling water reactors is that the first two reactors that India started using were boiling water reactors. The first two Indian reactors were boiling water reactors, and then after that we started using pressurized heavy water reactor. But before pressurized heavy water reactors, the first two reactors that India used were boiling water reactors. Now the efficiency of boiling water reactors is not as good as the pressurized heavy water reactors, and that's why we see that it's not a reactor that is used very often or used very widely. Then after that, one more reactor kind that we have is called as a fast breeder reactor. Now again, when we look at the fast breeder reactor is a kind of reactor. Just understand the words here. It is a fast breeder reactor. Why fast? Fast because it does not use any moderator. It does not use moderator. What was the role of moderators? To slow down the neutrons. This is a kind of reactor where we don't need to slow down the reactors. So because we don't want to slow down the neutrons, that's why we don't need any moderator. That's why it's a fast reactor. Right? It's a fast reactor because they don't use moderator. So that's why the fission is produced by fast neutrons. So this is basically why it is called as a fast reactor. The second term is breeder. So breeder comes from breeding. Breeding means to reproduce. So why are we using this term? It's being used because it is a kind of reaction, a kind of a reactor where you are able to produce more fuel than the fuel that you consume. So just imagine the situation where you go to a petrol pump and you get 500 rupees worth of petrol in your vehicle, and the same petrol can be used over and over again because that petrol is producing more petrol while your scooter runs. So that's a kind of utopia that we need want to live in. But that's unfortunately that's not the case, right? But in breeder reactors, we are able to make something similar very possible. That the reactor produces more amount of fissile material that it consumes in operation, means that it generates more new fuel than the fuel that it spends. Okay, it is able to produce more fuel than the fuel that it spends. So that's why it is called as a breeder reactor, because it in a manner is able to breed and produce more of its kind. It's able to produce more of its kind. That's why it is called as a breeder reactor. So this fast breeder reactor can be very crucial for the future of nuclear fission based energy, and that's why today we see that even in case of fast breeder reactors we have been working. There are two fast breeder reactors in India. First one is called as two fast breeder reactors in India. First one is called as a prototype fast breeder reactor. Right. First one is called as prototype fast breeder reactor. Now this prototype fast breeder reactor now has been operational for more than 20 years. Right. It has been operational for more than 20 years, and it has been generating the required energy for us for more than 20 years now. The second type of reactor that, sorry, please make this change. The first one, where it has been operational for more than 20 years, is called as fast breeder test reactor. Fast breeder test reactor. The second one, which is kind of under construction right now. So this is basically, I'll just write it here. This is operational for more than 20 years. All right, it has been operational for more than 20 years, and then now the second reactor that we are working upon is the prototype fast breeder reactor. Now, when it comes to the prototype fast breeder reactor, we have actually been waiting for a very long time now, so that we can get the services of the prototype fast breeder reactor. Almost 10 years back, it was 2012-13, when the opposition had asked a question to the then government, the UPA government, that what is the status with prototype fast breeder reactor. They said that it's almost ready. We perhaps will take 1 more year, and then prototype fast breeder reactor will be ready. Then, almost 10 years later, the opposition again asked the same question. This time, the opposition is the UPA, and they asked the government, the NDA government, the question that what happened, what's the status with the prototype fast breeder reactor? And this government also gave the same answer, that it's almost ready. Maybe just 1.5 years will be ready with the prototype fast breeder reactor. So that's why the government changed. The answer did not. So the thing with prototype fast breeder reactor is that it has been ready. As per the report, it has been ready for a while now. That almost since 2013-14, it has been ready. But there are certain safety concerns that have been flagged, and that is the reason why the operations have not begun yet. Because there are certain problems that we have encountered, and we want to make it safer. We don't want any kind of risk. So that's why there are a lot of certain modifications that are being made in the prototype fast breeder reactor to ensure the safety of this reactor. So until the time it can be ensured that it is 100% safe to use and there is no problem whatsoever, until then it will not become operational, and that is the reason it has not become operational according to certain reports. It's not an official answer as such by the government, but there are certain reports that have indicated towards this, that although it has been ready for a while now, but there were certain safety issues because of which there are modifications being made, and we are trying to make it as safe as possible before the operations can begin. So that's the status with the prototype fast breeder reactor. So in this scenario, operations haven't begun yet, expecting it to be we are expecting it to be operational very soon. So that's why this is the status right now that we have with prototype fast breeder reactor. So this is a typical design of a fast breeder reactor. Don't worry, you don't have to draw these diagrams at all. These are just indicators so that you can understand what's happening here. And it's very similar. It's very similar to what we discussed in others. Also, you have the same core, you have the same control rods, you have the same coolant and coolant being used here. Again, you have a steam generator which will convert liquid sodium into its steam. Then you have the same turbine, you have the same condenser, you have the same pump. So basically, the entire scenario is more or less the same as what we have seen in the last couple of reactors as well. So there's nothing as such. There's nothing to worry. And anyway, even if you don't know this diagram, it does not really matter in the examination hall. So these are the kind of reactors that India has been working on. Now, based on that, what we see is that we have been able to devise a plan, and this is India's nuclear program. Now, there are two questions to be answered when it comes to what is India's nuclear program. So the first thing is, what exactly is this program? And second question to answer is why? Why this program is needed? Why did we devise this program? And the second question is, what is this program? So now, first to answer the question of why, that why did we need a program like this? Why are we working on a program like this? So why? What is special with India's nuclear program? Okay. So when it comes to India's nuclear program, this is a program that was conceptualized in 1960s itself, and this was under the leadership of Dr. Homi Jahangir Bhabha. Now, when it comes to Homi Jahangir Bhabha, he has been one of the pioneer scientists for India, has been a significant scientist, especially in the early era after the independence that we got. We needed scientists like him to be functional and to be as aggressive as they were actually they were at the time of after the independence, because obviously the science budget etc. were very minimal, and still they were able to manage with whatever they could get, whatever money or whatever resources they could get from the government. They were still able to do a lot of things, and Dr. Homi Jahangir Bhabha was the one who devised a plan that would perhaps work for the next 60 to 80 years for India to be functional. So in 1960s, he came out with a plan that India will have a 3-stage nuclear program. The idea behind this program was that by the time we reach the third stage, we will be able to use thorium instead of uranium as our nuclear fuel. So why? That's why the answer to why is basically to use thorium in place of uranium as the nuclear fuel. Now, why thorium? Why do we want to use thorium instead of uranium? Yes, because of abundance of thorium. Because of abundance of thorium. See, we have a very limited quantity of uranium available in India, whereas when it comes to thorium, we have abundant amount of thorium. All right, we have abundant amount of thorium, especially in the monazite sand of Kerala. We know that we have abundance of thorium. And when it comes to how much thorium reserves that does India have, where do we stand in the world? We are at least in the top 5 nations of the world which have the thorium reserves. Some of the reports even say that India has the second largest deposit of thorium after Australia. So some reports say India is in the top 5. Some say India is the second highest. I would want to believe second highest story more. So if we go by those reports, you can say that India has second highest deposit, second highest reserve of thorium in the world. All right. So that's why we see that why we wanted to use thorium instead of uranium, because uranium, we do have uranium. I mean, you have some reserves in Jharkhand, you have some reserves in Andhra Pradesh, etc. So there are reserves of uranium as well, but very limited. So most of the uranium that we use today are imported. Most of the uranium would be imported from Central Asian countries or some of the other countries like the US or Canada or Australia, etc. We basically get uranium from all these countries. So we are dependent on these countries for our uranium needs, and getting uranium is not that easy, because uranium, everybody knows that uranium is not something which is usable only for electricity generation, but it's also something that can be used to weaponize it. That's why working on these kind of plans and having nuclear reactors in India, and especially just after independence, was almost an impossible task. A task that these scientists were able to do somehow, but it was a very difficult task. So just imagine, we got our independence in 1947. 1945, the entire world had seen the horrors of nuclear fission, the horrors of atom bomb, and the same uranium that you can use for electricity generation, the same uranium and getting plutonium out of it will be is where you will make the atom bomb, and you will be the world had seen the destruction, the kind of destruction that it could actually cause. So that's why, from that perspective, we do understand that it was not easy for India to even think of uranium in 1947, to think of nuclear fission in 1947, just 2 years after the kind of horror of atom bomb that the world had witnessed and what Japan had to suffer. So, so now that these scientists, they started talking about nuclear fission, and that we should start working on fission program, let's start working on nuclear reactors. All these kind of things nobody would listen to, because listening to these kind of things would mean a lot of backlash from the entire international community as well. But we knew the kind of advantage that it would give us, because we, I mean, after independence, the kind of energy requirements that we had, we could hardly support those kind of requirements. We could not support those requirements, whether the domestic requirements or industrial requirements. We could not meet anything. And this is where scientists like Dr. Bhabha, they started proposing that India should start working towards nuclear fission, because understand the value of nuclear fission, and with so little quantity we can produce so much. If you read the biography, there's a biography, I mean, written on Homi Jahangir Bhabha, where it has been all these incidents after independence also have been mentioned, that how he tried to convince the then Prime Minister Pandit Jawaharlal Nehru to start working towards nuclear fission, and the kinds of steps that he took on himself as well to ensure that nuclear fission can become a reality in India. And thus we see that with the help of Soviet Union at the time, we were able to actually establish some of the nuclear reactors in India. And he was working very fast. He was working very aggressively and very fast towards realizing the dream of using nuclear energy. And even in terms of, it is said that even in terms of atom bomb or nuclear weapon also, we had started moving in 1960s. And even a program like that also raised certain concerns with the US as well. US did not like it, and US never likes anyone rising to power. So US did not like it, and also the fact that India was getting closer to the Soviet Union was not taken very well by the US. And it is said that at that point of time, the US was also very closely following what is happening with the nuclear scene in India. That what exactly are we doing? Whether we are producing power, whether we are looking to weaponize and all that. The Central Intelligence Agency, or the CIA of US, the intelligence agency of US, they were very closely monitoring. It is said that they were very closely monitoring all the developments in India, and they were keeping a very close watch on Dr. Bhabha. Unfortunately, Dr. Bhabha died very early. It was, I think, 1967, when in a plane crash he lost his life. So he, somebody who was working very aggressively towards India's advancements in technology, especially in the nuclear arena, we losing him very early was a big setback for India. And that's why it is also said, many of the unconfirmed reports also say that it was not a natural death, it was not something that happened due to natural accidental causes, but something which was done by the CIA. That CIA was actually behind the death of Dr. Bhabha. In a manner, you can say that it was an assassination that they carried out, because India was working very aggressively towards its nuclear program. So unfortunate, but this is what perhaps happened then. But by the time he already had, you can say, laid the foundation of nuclear energy in India, that we already had a couple of nuclear reactors with the help of the Soviet Union. We already had started working on this nuclear program. The other scientists also knew how to work on the nuclear program, and we kept moving forward despite such a big setback that a very nascent country like India had within the first 20 years after independence. So the conditions then, I mean, speaking from what we were able to achieve, even though there were so many setbacks, is remarkable. That after 1947, we have a war in 1948 with Pakistan, then again in 1962 with China, then again in 1965 with Pakistan, losing our Prime Minister Lal Bahadur Shastri, who had started becoming very aggressive. So losing him, losing Dr. Bhabha very early at that point of time. So all these things happening at the time when we had started becoming aggressive, we had started growing, you can say, in a manner, would have set us back 50 or 100 years. But because of the kind of work that they were able to do, the kind of foundations that they were able to lay, it was very significant. And thanks to all of these developments, we were able to move forward despite these challenges. So this is why. So we could use thorium in place of uranium as the nuclear fuel, as India has ample thorium reserves, especially in the monazite sand of Kerala coast. Right? So that's why. Right? Now, what is the program? What is India's nuclear program? It is a three-stage program, where in the first stage we are using pressurized heavy water reactors. In the second stage we are using fast breeder reactors, and in the third stage we are going to use thorium-based reactors. So look at this. That this is what this entire reaction is about. Okay. So what we basically see is that first and foremost we will be using the conventional nuclear reactors, which basically are the pressurized heavy water reactors in the first stage, where we are using natural uranium. Now this natural uranium, while the experiment happens and while the splitting happens into barium and krypton, etc., a lot of energy is released, and there is this byproduct which is plutonium. The byproduct that we have here in this reaction is plutonium. Now this depleted uranium or used up uranium plus plutonium will be used in the second stage of the reactor, called as a fast breeder reactor, right? Fast breeder reactor, and from there on we get a lot of extra plutonium. So plutonium is used and we get plutonium. Now what we see is that here for the first time we also use thorium. We also use thorium. That is, thorium now for the first time is used in the second stage. Now remember that here thorium is not being used as a fuel. All right, thorium is not being used as a fuel. What we do here is called as irradiation of thorium. Irradiation of thorium. Alright, it is called as irradiation of thorium. So what is irradiation? Irradiation is when you pass radiations through something, is called as irradiation. Alright, so irradiation of thorium basically converts it into uranium 233. Irradiation of thorium converts it into uranium 233, and this uranium 233 will be used in the third stage. So in the third stage you'll have more of thorium. So we'll start introducing thorium, as you can see in a manner, as a fuel in the third stage, where this thorium will be converted to uranium 233, and these will also be breeder reactors, which are called as advanced heavy water reactors. Advanced heavy water reactor. And this reactor, once we start using this reactor, we ultimately see that this can be used for a very, very long time. So this is what we see in case of the three stages. So now just remember, and when you look at the data, you'll understand why these three stages have been used. So first question is, couldn't we use thorium directly? Was that a possibility, that directly have advanced heavy water reactors and start using it? Why to go through these two stages? The reason is that irradiation of thorium can be done in fast breeder reactors. So for that you first need fast breeder reactors, because your pressurized heavy water reactors can't do that. So because pressurized heavy water reactors can't do it, so you need fast breeder reactors. Now fast breeder reactors are using plutonium. So then could we have directly started from fast breeder reactors using plutonium? The answer again is no. Why is the answer no? Answer is no, because plutonium is not a natural element. Right? Plutonium is not a natural element. Plutonium is produced as a byproduct of the reactor in the first place. All right. So the pressurized heavy water reactors will basically produce will produce plutonium. Plutonium will be used in fast breeder reactors. Fast breeder reactors, the irradiation of thorium will happen. Then uranium 233 is produced. Even uranium 233 is not natural, so that's why in this reaction only uranium 233 will be produced, which will be used in the third stage as a fuel. So that's why ultimately, to get to the goal of using thorium, we need to start with using the natural uranium, that is uranium 235. So that is why these three stages are required. Otherwise, we would have done with the first stage itself. We wouldn't have bothered about going through these three stages. Now, the estimates are that if we use this for 30 years, if pressurized heavy water reactors are used for 30 years, okay, if we use this for 30 years, if we use this also for another 30 years after that, then the amount of uranium 233 that we'll have now will be enough to run this for easily for 500 years. All right, 500 years. So we can very easily use it for 500 years without having to worry about anything. So that's why we see that it's a very, very important stage for us, that once we are able to get to the third stage, we'll be able to use this. So advanced heavy water reactor, or there is one more reactor which is called as Indian molten salt breeder reactors. All right, these are the two types of reactors that we are using in this. So now, Indian molten salt breeder reactor also has a very interesting story, that in case of these two reactors, and we'll discuss briefly about these two reactors as well. So these two reactors, advanced heavy water reactors and the Indian molten salt breeder reactors, we see that these are reactors that are under construction right now. It's not ready yet. Both of these are under construction. Now, what we see is that in these kind of reactors, we are able to use them in a much safer manner as compared to pressurized heavy water reactor. One of the reasons, now this might not be very surprising for you, but one of the reasons why everybody keeps using pressurized heavy water reactors even today, pressurized heavy water reactors, just know this, pressurized heavy water reactors are the most unsafe reactor designs. They are the most unsafe reactor designs, prone to accidents, prone to meltdowns, prone to creating a lot of nuclear waste. Yet the world keeps on using pressurized heavy water reactors. The reason is plutonium. That you produce a lot of plutonium from the same reactions, and the same plutonium can be weaponized. So the byproduct basically is your fuel for atom bomb. The byproduct of this reaction is your fuel for atom bomb, and that's why pressurized heavy water reactors. That's why the world is so keen to keep using pressurized heavy water reactors, because everybody knows that you can very easily weaponize pressurized heavy water reactors. Few years back, if you remember, there was something called as WikiLeaks. Have you heard of WikiLeaks? Yeah, heard of it? So for those of you who haven't heard, WikiLeaks basically had leaked a lot of confidential documents of the US government. Right? A lot of documents that the US government had kept as secret, those were leaked by WikiLeaks. And once it was leaked, a lot of information that was never supposed to come out, they all were leaked. Now, in one of these cases, what has been revealed is that the US in 1950s itself knew about molten salt breeder reactors. Molten salt breeder reactors which are safe. Molten salt breeder reactors that do not produce plutonium. Molten salt breeder reactors that are safe to use, not prone to accidents, no radioactive waste, yet it was kept as a secret. Why? Because it does not produce plutonium. So why would you use something that does not let you weaponize your nuclear fuel? So that's why even though they knew that they could use molten salt breeder reactors and that's a safe design, it's a peaceful usage of nuclear energy that the entire world always keeps on preaching about, yet they never used it. And they never used it because they knew that if they start using it, it would mean that they will always have to use it and they can never go back to a pressurized heavy water reactor that gives them so much of nuclear energy and at the same time gives them a lot of nuclear weapons. So while they were talking about nuclear non-proliferation treaty and asking the entire world to sign those treaties so that you can use, you are only allowed to use nuclear energy for peaceful purposes, they kept a secret so that they could keep on weaponizing their nuclear energy. So unfortunate, but the truth of the world. So this is basically what happened. But surprisingly, the countries which always have been the target of the Western countries, whether US or the European countries, etc., India and China. India and China are two countries which are working on these safer designs so that we can actually peacefully use nuclear energy. So molten salt breeder reactors. Molten salt breeder reactor is one of those ways in which we actually can make the nuclear designs actually safer, and they would become safe because this time what we see is that there is something called as a fluoride based salt. There is a fluoride based salt that we are using in the molten salt breeder reactors. Now what happens is that molten salt, right? So salt which has been molten, generally we know that salt is what? Salt is in a crystalline form. You use common salt, forget about fluoride salts and all, you use common salt. So the salt that you use, can you liquefy it? Have you seen liquid salt? I mean, let's say if you simply start to heat it, does it convert into liquid? It doesn't, right? It converts at a very high temperature. Correct. So under normal conditions, it will be a crystal. It will be a crystal. So what happens is that there are special conditions under which you can melt it. Now, if those conditions don't exist, what happens? It will crystallize. So if it crystallizes, it stops the reaction. I mean, if you think about a molten salt, it will work in a very similar manner as a common salt would work for you. That if you have a very high temperature, then you can melt that salt. Otherwise, salt will remain in its crystal form. So if the temperatures decrease, if let's say those conditions are not met, it will quickly cease to react. So reaction will quickly stop, and that's why it will not have any meltdown, any accident, any leakage, any radioactive waste. All those kind of issues do not exist in this particular manner. So that's why we see that we ultimately are trying to use this these kind of reactions, these kind of things, so that we can make the reaction safe. So this is what India's nuclear program has been all along, where we have been trying to use these three stages. So use these three stages so that we can actually work on our programs and we can get to a stage where we can keep using thorium. We can keep using thorium so that we do not have to worry about our energy security in the future. Now, one of the issues here has been nuclear waste disposal. So nuclear waste disposal, because there are radioactive wastes that are generated after the reaction is done, because largely we are still using pressurized heavy water reactors. So because of the use of pressurized heavy water reactors, we know that radioactive wastes are produced here. Now the waste that we produce will be classified into two parts: low level radioactive waste and high level radioactive waste. So low level waste basically are the ones which are not very harmful for us. Right? Low level wastes are not really harmful for us. So that's why we are using these low level radioactive waste, can be disposed very easily. We can use landfills, for example, and dispose them. But high level waste are the ones which are dangerous, which can have health implications and can have implications for the environment as well. So that's why in case of high level waste, extra precaution is taken to get rid of that waste. So for example, we see that they would be solidified into a leach resistant form such as a borosilicate glass, and this process is called as vitrification. This process is called as vitrification. So in case of vitrification, what we do is that all this nuclear waste that we are generating, it will be captured in a borosilicate glass, or a kind of, let's say, it's a kind of glass that's not very easy to degrade. It will last for a very long time. The action of bacteria or the decomposers, etc., will not decompose it easily. So what we do is that we take this high level waste, pellets of glasses, it will be captured in pellets of glasses, and then it will be buried deep underground. There will be nuclear facilities that will have, there will be special waste disposal facilities that we have in India where all these disposal of high level waste is done. So in this manner, we first classify into what is very harmful and what is not, and the ones which are not harmful, the normal methods of disposal will be used, and the ones which are harmful will be using special methods to dispose them. Then lastly, the last topic for us is application of nuclear technology. So we understand that application of nuclear technology largely is in electricity, correct? The most important one is generation of electricity. So whether with the help of nuclear fission, whether with the help of nuclear fusion, but ultimately our first goal has been to use it for electricity, correct? So whether fission or fusion, the first goal is to use it for energy, for electricity. But apart from that, we do see that there are other ways in which we can make the use of nuclear technology. For example, in agriculture. So in agriculture, we see that in water and soil management, in pest control, in ensuring animal health and productivity, in ensuring food safety. In all these cases, basically, we can make the use of radiations. We can make the use of radiations to destroy microorganisms. To destroy microorganisms, because of the action of microorganisms, we might see that some kind of contamination may happen, or even let's say to increase the longevity of the produce for the food. For example, let's say the fruits and vegetables that are going from the farm to the market, from the market to your houses, it takes a lot of time, right? So in that time, a lot of it might also get destroyed. It might also start to become stale. It might start to become unusable for us. So there also we see that controlled amount of radiation. All right, I'm writing this: controlled radiation. Controlled amount of radiations can be used to destroy microorganisms. So we can also, so food safety, we can increase the shelf life. Increase the shelf life of the food. Not only that, even in case of seeds, increase the shelf life of seeds as well. To do that as well, we see that controlled amount of radiations can be used. Apart from that, one more can be the nuclear fertilizers. Nuclear fertilizers. So for example, we have nitrogen 15. We have nitrogen 15 that is also used. So this nitrogen 15 helps us understand the optimum use of fertilizers. That what is the absorption rate of the roots. That how much of nitrogen 15 is getting absorbed by the roots of a plant is something that nuclear fertilizers help with. So that you can use the amount of fertilizers accordingly. Neither overusing the fertilizers, because overusing the fertilizer can have a negative impact on soil quality. And if you are using lesser fertilizers than required, it means that optimum growth of the crops will not happen. So to strike a fine balance between the two, we sometimes use nitrogen 15, and it helps us in determining the amount of nitrogen or amount of nitrates, etc., that can be used as fertilizers. So that's why nitrogen 15 can help in optimize. It can help in optimizing. Nitrogen 15 can help in optimize the amount of fertilizers used. Right, so that's why it can become very, very crucial from that perspective. Then there is something called as carbon dating. Now, in case of carbon dating, we basically are able to accurately date the historical artifacts, meaning that what is the age of the historic artifacts, we'll be able to find the age with the help of carbon 14. Now, what happens here is that up to 50,000 to 60,000 years old articles, we can actually use it. So, for example, and how we are able to do that? Anything, for example, let's say we are trying to find the age of a fossil or something that we have found some an organic form, maybe a part of plant or animal, whatever it is. So now, while these plants and animals are living, while these have been used, the ratio of carbon 12 to carbon 14 in anything that is living is always fixed. All right, ratio of carbon 12 to carbon 14 is fixed. Once it ceases to live, once it dies, the carbon 12 amount is now fixed forever. Carbon 12 amount is fixed forever, but carbon 14 is radioactive. Carbon 14 is radioactive, and because it is radioactive, it will keep reducing in its amount. It will keep losing some particles because it is radioactive. It will keep losing some particles, and while losing the particles, it will keep on decreasing in its amount. So there is a concept of something called as half-life. There is a concept called as half-life. So half-life is time, the amount of time in which a nuclear material reduces to half of its original mass. All right, reduces to half of its original mass. So now, what happens with carbon 14 is that this carbon 14 has a half-life of almost 5,700 years. All right, almost 5,700 years, meaning that in 5,700 years, if there was 100 grams of carbon 14, now it would have reduced to 50 grams of carbon 14. So from there, we do the calculations and find out what would have been a possible age of this artifact that we found. So that's why we use carbon 14 here to find out this age. Then in also improving public safety, we see that there are multiple different ways in which nuclear material can be used. So we see that, for example, in making runway lights, we are making the use of the nuclear material. In pacemakers, in smoke detectors, in all these cases, we are making the use of these nuclear radioactive elements. Many of these radioactive elements will be useful in a variety of ways. All right, these will be useful in a variety of ways, and hence we have been using them in a lot of different ways. So, and there's a list. I mean, there is not one, but there are multiple ones which are used in multiple ways. So, for example, not only in this, even in industrial ways, we see that it is used. So, for example, to test the strength, in all these cases, we see that to test the strength of material as well, we can basically make the use of radioactive elements. So, that's why we see that, for example, let's say something like cobalt, that we have cobalt 60 that can have that has medical applications, but can be used in industrial applications as well. That it will also be very, very helpful there. And so similarly, we see that we discussed about smoke detectors. So there is americium which is used in smoke detectors. So we see that there are a lot of these which can be used in one ways or the other. So in industries it is used, in medical applications it is used. In medical applications also, for example, radiation therapy, treatment of cancer. There are radioactive medicines that are used in a lot of ways. In radioactive, in imaging also there are different types of radioactive elements that are used. So for example, krypton can be used. We even something like technetium can also be used. So there are a lot of these radioactive elements that can be used in medical applications as well. So where it talks about radiation therapy or radiology, treatment of cancer, where we try to kill the cells which have become cancerous. So killing these cells happens with the help of these radioactive elements, where these radioactive elements will release gamma rays, and controlled amount of gamma rays are released so that we can kill all these cancerous cells. So there are multiple different ways in which these radiations can actually become useful. And then there is something that now ISRO has started working on, and this is basically radioisotope thermoelectric generators, or RTGs. So in case of RTGs, we basically are using the radioactive isotope plutonium 238. So plutonium 238 will be used for power generation, and we see that for power generation, where you are going into, let's say, a deep space mission. So in a deep space mission, there is no solar energy. So for example, in case of Chandrayaan, you might have seen that the rover is working on solar energy, and now it will be put to sleep because now there will be no solar energy available for, let's say, almost next you can say 14 to 17 days. Right? So almost 20 days. Almost 20 days there will be no solar energy. So that's why now it will become defunct. So in cases where you are near the sun, you can use solar energy. But when you have a mission where you are going into a deep space mission, then in that case, solar energy is no more useful. So then nuclear energy comes into the picture, and this is where ISRO now also has been working. So there are multiple applications like these where nuclear technology can be used. What I'll do for you, I have made a list of important radioactive elements, and their usage. So just know this, because just in case they have to ask a question in the prelims examination, they can actually do that. So list of the most important, the most widely used radioactive elements. I've made a list of them. I'll just share that list with you as well as a part of the additional reading material, so that you can make the use of all these especially for your prelims examination. Right. So this is the end of this particular chapter. Let's take a break here, and after the break, if you have any questions, please keep posting all the questions. After the break, first I'll take all your questions, and then we'll begin with our next chapter, that is biotechnology. All right. So time is 7:47. So let's be back by 8. And then we shall begin with our discussion on biotechnology. Welcome back, everyone. Let me take your questions first, and then we shall move ahead. How fast breeder reactors end up producing large amount of fuel than it consumes. So basically, it's an entire process that we have set up in the fast breeder reactors, where there is an exchange of protons and neutrons that happen. And with the help of these exchanges that we see that first there will be a lot of energy that will be produced, and as a part of the second part of that reaction, again certain conversions back into the original fuel happens, and then we see that the same original fuel is converted back. So in this manner, I mean, I'm just trying to very oversimplify the process. Otherwise, in fast breeder reactors, there's an entire procedure that is carried on, so that there are multiple conversions from one element to another, one radioactive element to another that happens, and ultimately we get back to where we started from. What are the normal methods of disposal? Normal methods of disposal is how any solid waste management happens, where all the waste will be segregated and accordingly they'll be disposed. So, for example, plastics will go somewhere, glasses will go somewhere, anything that is disposable will go somewhere else. So, in this manner, the segregation will be done, and then the disposal will be done. But in case of high level waste, the process will be very different. Keeping radioactive waste into borosilicate is just keeping it farther away from us. Is it a better method? So yes, you can say that. I mean, we are trying to keep the radioactivity levels down, and we are trying to keep it away from getting, so that nobody gets exposed to them, because we know that there are radiations that they will keep on emitting, and that can be very dangerous for our health. So hence we see that in these kind of cases we are always maintaining a distance, and that's why borosilicate glass, and that too deep inside the earth. Why ARMs have a lot of long answers? I mean, ARMs are for additional reading, so that's why, I mean, there are certain additional information that we have given, so that even if, let's say, as I told you, that in outside whatever we are discussing here in the classroom and the current affairs, even if you don't go anywhere, it doesn't matter. But if you want to read additional information, you don't need to go to any other source, but just the additional reading material that will help you. Now the space policy, I'll just check. I'm sorry, what I don't know, but I'll just check if there's any problem there. Every PPT, 50 pages from PPT, how to make notes, how to know that which line we write, or you don't need to write anything. I mean, whatever is there on the PPT, it's already there, and additional information I keep on writing, so you don't need to write anything extra apart from that. So you don't need to worry about it. Due to Earth's gravity and to need more thrust, we usually use solid propellant at the core stage of the satellites. Then why the Vikas engine is used in the GSLV Mark III core stage? So in the core stage, see, core stage is an additional stage. Apart from the first stage that we have, the first stage is always solid. The core stage is an additional stage. So that is for additional fuel requirements. So that additional fuel requirement can also be taken care of with the help of liquid propulsion as well. So that's why Vikas engine is used there. Please say what to read. I'm referring to annotations only. That's enough. That's what I said. Whatever is there on this PPT, right? Whatever is there on this PPT is enough. Just keep on adding current affairs to it, because it's still 9-10 months away from the examination. So keep adding current affairs to it. Additional reading material is for additional reading. I'm not saying that the questions will come from there. Wherever the questions can come from, we already are discussing that from in the classroom itself. So there is nothing that has been left only for your reading. It's for your additional reading. If you want to read more, read it. Just making it easier so that you don't have to go to 5 different sources to just read about whatever if you need any extra information. Then why Fukushima waste disposal in Pacific? Why not underground? That's why there's so much of controversy when Japan said that we are going to release all these waste, although these are treated waste, but we are going to release it into the Pacific. That's why there is so much of controversy that happened here. That you should take care of your own disposal instead of just dumping it into a shared water resource that may potentially have a negative impact on the marine ecosystem. So that's why there is so much of controversy that also happened there. Why GSLV used in Chandrayaan mission but PSLV is used in Aditya L1 mission even though the sun is farther? So the basic structure of what I told you was that if the satellite weight is less than 1500 kg, you can use PSLV. If it is beyond 1500 kg, you can't. Aditya L1, this is something that we had discussed, right? Aditya L1 is how much? 1400 something, correct? Chandrayaan 3 is how much? 2200 something. So a 2200 kg satellite can never be launched with the help of PSLV. A 1400 kg satellite can be. So that's why we are using PSLV XL for Aditya L1, and we can't use PSLV XL for Chandrayaan 3, and hence we use GSLV Mark 3 there. How nitrogen 15 helps in optimizing the amount of fertilizers. So basically, nitrogen 15, because it is radioactive, it will also keep on losing its particles. It will keep on releasing its particles. So how much is absorbed versus how much is released is something that we calculate, and we get to understand what is the rate of absorption. So based on that rate of absorption, we can calculate how much of fertilizer should be used for a certain crop. But is it safe, the Fukushima water? What Japan says is that it's completely safe. Because they said that they have completely done every kind of treatment that is required for that water, and after that only they are releasing it into the Pacific. But still, I mean, you can never be very sure that it will be completely safe. Saying that it will be completely safe will be a little extreme, but this is what they have claimed. When plutonium is used in fast breeder reactors, then why do we need to dispose it as waste? We don't want to. We don't want to dispose it as waste. We do use it, but what happens is that the quality of the fuel matters. So what we see is that even though it is the same element, it is the same, let's say, plutonium 239 element, but the quality of that 239, if it is good enough, then it qualifies as fuel for second stage. If the quality is not good enough, then it goes for disposal. So this is something that we also do as a part of nuclear fuel cycle. That at the end of nuclear fuel cycle, we see that this kind of a treatment can be done. We first take a decision based on whether a reprocessing of this fuel can be done for second stage or a disposal needs to happen. So it depends on the quality of the fuel or the quality of the byproduct that we get out of the first stage. Please summarize stage 2 and 3. So what we are saying is that in stage 1, we are using uranium. By using uranium, pressurized heavy water reactor based reactors are used. A lot of energy will be produced. As byproducts, we produce plutonium. This plutonium will be used in the second stage, where we have a fast breeder reactor. So plutonium is used, and because it's a breeder reactor, more of plutonium as byproduct will also be produced here. While what we also do in the second stage is that we are introducing thorium. Now this thorium, with the help of the reaction that is happening, thorium will be converted into uranium-233. Thorium-232 converts to uranium-233, and this uranium-233 becomes the fuel for the third stage. So in the third stage, which is again a breeder reactor, uranium-233 will be used, and thorium continuously will be introduced here, which will be converted into more of uranium-233, and hence we see that this continues. Where to study about rare earth materials. See, rare earth elements are very special elements where we see that it's not really that they are all rare, but their composition, their availability in a lot of areas is pretty limited. So that's why they are called as rare earth elements, and there are certain areas where they are useful. We have been able to we have been able to find certain use of them. So for example, cerium is there or lanthanum is there, and these kind of materials are used there. So overall, we see that they can be used in multiple different ways, especially in electronics. We see that in electronics, these rare earth elements are used. In sometimes we also see that in photovoltaic devices also it can be used. In certain cases in defense also we see that we find certain use of all these rare earth elements. So not particularly, you don't need to read about them specifically unless they are in the news. Please explain about G25 star. So G25 star, basically, when we say G25, so G25 star is on the basis of the size and the temperature of the star. G2 basically comes from the temperature. G2 is about temperature. So when the temperature is in the range of 5,000 to 6,000 degrees Celsius, you say that it is a G-type star. So because Sun has a temperature of approximately 5,500 degrees Celsius, it is classified as G2. And 5 basically comes from its luminosity. Luminosity, or you can say the size. Both are related. So size being 5 means that it is neither very high nor very low, because it is from 1 to 7. So between 1 to 7, 5 is in the mid range, and hence we say that it's a G25 star. So we call the Sun as the G25 star. Hope it explains. Can you please repeat why irradiation of thorium is done? Irradiation means to basically pass radiations. So when we pass radiations, you have thorium 232. All right, you have thorium 232, and this converts into uranium 233 with the help of irradiation. So irradiation is nothing but passing radiations. So radiation, because there are radiations already in the reactor, right? Because you are using plutonium, so plutonium is used, and there is the core where the nuclear reactions are happening. So you have all the beta and the gamma and the alpha rays there. So those radiations are passed through thorium, and it converts from uranium 232 to from thorium 232 to uranium 233 by absorbing extra neutrons and protons. In this way, if we get to thorium reactors, there will be no nuclear waste. No, there will still be nuclear waste, but not the dangerous ones. The dangerous ones that we get right now in pressurized heavy water reactors, those kind will not be produced. Still, they will see what happens is it's not that it's completely 100% of the byproducts do not convert into the reactant. There will be some which will still be a waste, but the waste, the danger levels of the waste will be pretty low as compared to what we see in pressurized heavy water reactors. How India's nuclear program is different from other countries' nuclear program. So every country, according to their needs, they have devised their plan. So our plan is completely based on thorium. Other countries, they do not have thorium, so they don't have a thorium-based plan. They simply are using uranium wherever they can. Magnetic and inertial confinement. Very simple. When you're using strong magnetic fields for nuclear fusion, it is called as magnetic confinement. Something that happens in the sun because it has a very strong magnetic field. Inertial confinement when you use lasers, because with the help of lasers you can drive the plasma close to one another. So that is called as inertial confinement. Irradiation also used in food processing industries. Yes, absolutely, it is used. The objective test posted on the weekend, there was some problem with the answer. Something else was in the explanation and answer. There was a difference. I'll have a check. I'll just check it. There could have been a problem. Difference between GSLV Mark 3 and LVM 3, there is no difference. It's just the names. They have, you can say, updated the name. First they used to use GSLV Mark 3 as a name. Now they say that it is LVM. So there is no difference. How molten salt breeder reactor is safe and how it does not melt. So see, the salt that we are using is fluoride salt, molten fluoride salt. That becomes the coolant that is used basically in the reaction. And overall, what happens is that because at normal temperature and pressure, these would be crystalline form. So that's why if those conditions are not met, it will very quickly just convert into crystalline form and stop the reaction from happening. So that's why they become safe. And the radioactivity that is produced in pressurized heavy water reactors, those do not exist there. Now I've already taken your question. I'm not avoiding anybody's question. I've already taken almost 20 minutes to answer everybody's question. Nobody's question is getting avoided. I'm trying to read as many questions as I can. There are some questions which are repeated questions. Many of you have asked very similar questions. So there I've just combined all the questions and given you the answer. Otherwise, it's not that somebody's question is getting neglected at all. Disadvantages of nuclear tech. So disadvantage-wise, the problems are with the radioactivity. The radioactivity can be bad for health, can be bad for the environment, can be very dangerous. It can lead to nuclear accidents, it can lead to nuclear wars. So those are the issues that we have. So more than disadvantages, these are issues that we have, not the disadvantages. And it's all up to us. If we can control all those problems, then it's a wonderful technology to use. Main questions I'll take. I'll just take two of the subject. I mean, two of these areas together: space technology and nuclear. Sorry, energy as a chapter. Both I'll try to take together. Most probably I'll take it tomorrow. All right. So let's move forward. I've taken a lot of questions. Still, if there are questions that you've posted and they're unanswered, let's take it at the end of the session today. Moving on to the next topic, the next chapter for us is biotechnology. Now, in terms of biotechnology, first from prelims and mains perspective, again, it's a very, very important topic. Every year in the prelims examination, we do see that a question comes from here. And if not every year, at least every second year, at least every third year, one question does come in the mains examination as well. Questions at the mains level, whatever they have asked until now, have been very, very easy. And at the prelims level, questions at times have been challenging. So understand what kind of questions are asked in prelims versus what kind of questions are asked in the mains examination from biotechnology. At the prelims level, what we have seen is that most of the questions that they have asked in the past, most of these questions, they have been based on certain concepts or certain words. I mean, concept-wise, some of the basic concepts related to what is biotechnology, what is DNA, the role of genes, etc. These are the things that they have asked in the past when it comes to the prelims examination. And there are a lot of word-based questions. Word-based questions meaning where they have just given one word and they have asked you a meaning. Simple. I mean, these are words that many times just by breaking down the word, you'll be able to answer that question or you'll get some hint of what that answer should be. This time also, for example, 2023, there were two such questions which were asked. The context was some of the discoveries and the Nobel Prize of last year. The context was that. But even if you, without knowing the context, without knowing the current affairs, even if you try to break down the word, if you know the meaning of the parts of the word, you'll still be able to make out what the answer should be. So many of these questions, they're just simply word-based questions that they ask. Otherwise, some of the conceptual questions have been asked in the prelims examination. In the mains examination, the questions have been more of application-based questions, based on health applications, agricultural applications, use of biotechnology in one way or the other. So questions have been fairly simple at mains level, but at prelims level, the questions have been a little more difficult. We'll also take the examples of what has been asked in the past, but this is how it is. As a chapter, not a very big chapter as the first two chapters have been, but still the concepts, the limited number of concepts that we are going to deal with, questions do come from there every year. So biotechnology, we have two words, biotechnology. Bio basically comes from a word called as bios. Bios is where you also derive the word biology from. So when we say bios, bios basically means life. Right? Bios means life. So that's why biology is the study of life. The study of the living forms is called as biology. So bios means life. That is where we are deriving this word from. And then you have technology. What is technology? We are studying about the subject called as science and technology. So can you tell me what according to you is technology? Yeah. So a basic definition, as many of you have mentioned, would be application of science. Correct? In a very basic manner, we can say that it is application of science. And then what many of you have mentioned, for example, ease of life or making our life easier, application of the latest knowledge, innovative methods for better utilization of available resources. Wonderful way to put things. So these are ways in which you can see. So in a very simple, a very trivial way, I can say that it is nothing but application of science. Correct? So whether it is latest innovations, whether it is being used how to make our lives easier, or utilizing the resources, a proper utilization of resources for our benefit. So in each and every one of the cases where we are applying science in one way or the other to get something, to get some kind of application, some kind of use, it will be called as technology. So now combining these two, when we say that it is biotechnology, biotechnology can be an application of science in terms of life. So when we are using anything living, all right, when we are using something which, when we are using a living organism or a process related to a living organism for some kind of application, we can say that it is biotechnology. All right. So living organism or a process of living organism for some kind of application will be called as biotechnology. So in simple terms, this is how we can define what biotechnology means. There are multiple definitions. I mean, if you go on Google and if you just start browsing through the various definitions, you'll find more than 50 definitions out there. But just remember basics. What the basic is, when we are using living organism or any process in any living organism for any application, we can call it as biotechnology. Now, the use of biotechnology has been something that we have been able to do for maybe 1,000 years or more. For example, something as simple as making curd from milk. So making curd from milk is an example. Where what do? You take a bowl of milk, add 1 spoon of curd in it, leave it overnight. Next morning, you'll see that now milk has converted into curd. How does that happen? Because of action of certain bacteria called as lactobacillus. So that those bacteria, they convert milk into curd. Right? They get a medium in which they can reproduce, in which the breeding can happen, and this is where they keep on converting milk into curd. So within maybe 6 to 8 hours of time, you might perhaps see that milk has converted into curd with action of these bacteria. So that's why we see that this is something that we can see, and this is biotechnology. Why is this biotechnology? Because we are using a living organism, which is a bacteria, for an application that is converting milk into curd. So we have been using biotechnology without knowing that we have been using biotechnology for thousands of years. Preservation techniques, where also some of the natural resources have been used. So those preservation techniques also have been the use of biotechnology. The process of fermentation, where you make alcohols, that also is a process of biotechnology. Fun fact is that fermentation as a process, making alcohols, has existed before we started learning how to make the curd. So you can say that for humanity, the priorities have been straight. That first we learned how to make alcohol, and then we started to understand how to make curd. So later we understood, okay, fine, similar process can also be used for making curd. So there are multiple such processes. The use of yeast to make bread, that also has existed for a very long time. So all these, you can say, are processes where we are using some kind of natural resource for some kind of application. So that's why it all can be called as biotechnology. But then when we study biotechnology today, we are not talking about these kind of approaches, which were more of a hit and trial approach. That something happened which led to something. We are not controlling that. We were not trying to control that environment for our requirement, right? So many of those things might just have happened by chance. That something may have happened. Let's say the fermentation process may have happened by chance. Making of curd may have happened by chance. So those kind of things might have happened by chance, and we just stumbled upon it and we found a use for it. But when we talk about modern biotechnology, the biotechnology that we're using today, that's very different. The modern biotechnology, where we are using genes, where we are using our knowledge of the DNA for making something, where we are doing something with a purpose, where we have a reason why we are doing something. That's very different, and that's something that has developed only in the last 50 to 70 odd years. Because until 1950s, we did not really the discovery of DNA had not happened. All right, the discovery of DNA happened in the 1950s, and that led to, you can say in a manner, the birth of modern biotechnology that we basically are going to study in this particular chapter. So first and foremost, we know that biotechnology comes from two words. You have bios and you have technology, and you can say that it can be defined as the application of living organisms and their biological processes in order to make the best use of organisms and not microorganisms, the best use of organisms for the benefit of humankind. So in this manner, we see that this is how we can define what biotechnology basically means. Now, as I told you, our understanding of biotechnology today, when we talk about modern biotechnology, comes from our understanding of the DNA. And there are three terms that become very crucial for you because they will be very often used terms in this chapter and in the context of this chapter. So, what do we mean by DNA? What do we mean by genes? And what do we mean by chromosomes? And the differences between them. So, when you understand a living organism, let's say if we are talking about an organism, if we are talking about an organism, there are two ways in which we classify the living world. One, above the level of organism, and then below the level of organism. So, for example, above the level of organism, we know that organisms lead to populations. And populations basically will form communities. And communities will form the ecosystems. So this is how the things work, that they will form the ecosystems, and thereon you have the biomes and the biosphere, you can say. So in this part you can say is the environmental organization or the ecosystem organization. So this is one level of organization where ecosystem, and lastly, I mean, if you have to write, you can say that the last one here is biosphere. Right, so this is one level of application. The second level is when we start going below the organism, inside the organism. So this organism would have been made of organ systems. These organ systems made of organs. These organs made of tissues. So organs are nothing but the set of tissues which do or carry a specific function in your body. The tissues would be made of cells. Right? Now we say that cell is the smallest structural and functional unit of life. Smallest structural and functional unit of life, meaning that it is the smallest structure, meaning that structure-wise it is the smallest unit of life which can live on its own, which can do all the activities on its own. So that's why smallest functional unit of life. All right. Now when we go inside the cell, the cell has its own world. All right. The cell has its own world. So here you basically have the biological organization. Now when we go inside the cell, there are various cell organelles. And all these organelles, they have their specific function. For example, mitochondria to provide energy to the cell. Then after that you have cytoplasm to provide a base to the entire existence of everything. You have ribosomes which help in protein synthesis. Similarly, we have something called as nucleus, and this nucleus is also called as the brain of the cell. Why? Because it controls and coordinates all the activities in the cell. Everything that a cell does will be controlled by the nucleus, just how as our brain controls everything that we do. Everything voluntary and everything involuntary. Everything that we do is controlled by the brain. Similarly, inside the cell you have this nucleus, and this nucleus will be called as the brain of the cell because it controls and coordinates for all the activities inside the cell. Now, inside the nucleus, we have some pairs of chromosomes. Okay, we have pairs of chromosomes. Now, these chromosomes are made of DNA. But before that, we have something called as genes, which are a set of DNA, that perform a function, right? Which perform some kind of function in the body. And then these genes, a combination of all these genes, will make certain pairs of chromosomes in the body. So in this manner, we see that this is how you have another structure that you have. This is, you can say, is the genetic organization. All right. In a manner, if I want to call it, I can say that it is this one. I can call as genetic organization. So this is the structure. All right. This is the structure of the cell. Now, in this manner, we have the three: DNA, genes, and chromosomes. So just try to understand what do we mean by these. What is a chromosome? What is a gene? What is a DNA? How are they different? Why this organization is required? So first, we have chromosomes. So in case of a chromosome, we say that these are long, coiled up, thread-like structures. They are made of DNA and protein. And all the genetic information that we have in our body, all that information is contained in the chromosomes. So for example, when it comes to humans have 23 pairs of chromosomes. So 23 pairs, meaning that a total of 46 chromosomes, out of which 22 pairs are common in both males and females. All right, 22 pairs are common in both males and females. The 23rd pair is different in males and females, and that is what differentiates between who is a male and who is a female. So that's why we say that these are 22 pairs of autosomes, which are non-sex chromosomes, and one pair of sex chromosomes, which determines the sex, whether somebody is a male or somebody is a female. So these are chromosomes, and these chromosomes are made of coils of DNA that will also first make up the genes. So what are genes? These are segments of DNA that contain the instructions for development and functioning of the living organism. Now, what we see is that these genes, they will be carried on from one generation to another. So what we are saying is that these are segments of DNA. All right, these are segments of DNA. So segments of DNA together, they combine and they form a kind of a gene. And this gene will have certain characteristics. So for example, every physical attribute that we have is because of some kind of gene in our body. So for example, color of our skin, color of the eyes, the height, or let's say how many hairs will remain in my head, or whether I'm going to lose my hair or not. All these things are genetic in nature. Many of these things are genetic in nature because these are the genes that are being carried from one generation to another. So if there are these genes that will ensure that I keep losing hair very early, I can't help it. So no shampoo or nothing will help. It will happen. You can delay it, you can do something about it, but ultimately this will happen. So all these are properties, right? All these are characteristics that are genetic in nature, that are carried on from one generation to another. So genes are nothing but a set of DNA together which perform a specific function, which have a specific characteristic in us. So that will be called as genes. So that's why they are called as basic units of heredity, and they are passed on from parents to the offspring. And there are various different variants, or called as alleles, which can result in variations in the traits such as the eye color, hair color, height, etc. So now what we see in these kind of genes is that there are these variations that can also come in because of the combination of the genes that are coming between the father and the mother. Because ultimately, let's say if you're talking about humans, then we know that the method of reproduction that we have in this, there is a mixing of the DNA that happens between the males and the females, and that's why there is a unique set of genes that will be produced in the offspring, where there will be some genes that are borrowed from the mother, and there will be some genes that are borrowed from the father, and hence the offspring or the child would be a combination of these characteristics both from the mother and the father. So these are genes which are segments of DNA. So it's a molecule that carries the genetic instruction used in the growth, development, functioning, and reproduction of all the living organisms. And that's why we say that it's a blueprint for all our cells, and all the information that is needed for building and maintaining our body and our lives. All these things are there inside the DNA, and they are made of 4 chemical bases: adenine, guanine, cytosine, and thymine. So A, G, C, T. and they basically are arranged in a certain sequence so that they can actually form genes. So if you see this, if you look at this particular picture that we have right here, we have adenine and thymine which always combine together, and we have guanine and cytosine which always combine together. So you make an AT from here and you make a GC from here, and now they would combine in various different forms. So for example, it can be ATGC that you produce, it can be TAGC that you produce, or it can be TACG, or it can be ATCG, and so on. So these kind of combinations can happen, all right? These kind of combinations can happen, and all these combinations again will combine in a manner that they form a gene, and this gene will have a particular function. This gene will have a particular characteristic. So DNA basically carries the instruction. There is another information carrier along with DNA which is also called as RNA. So DNA, which is also called as deoxyribonucleic acid, there is something which is called as RNA, that is ribonucleic acid. Ribonucleic acid also carries instructions. It carries instructions for making the proteins. In making the proteins, it has instructions which will make various different types of proteins in the body, and that's why they will be formed all across the body. Whereas when it comes to deoxyribonucleic acid, which is a more specialized form, is found inside the nucleus. All right. So DNA is found only inside the nucleus, but RNA can be found elsewhere as well, because the other proteins that are being made in the body for the various activities in the cell, they all will be done with the help of RNA. So there are certain differences, and from the prelims perspective, you should notice that what are the various differences that we have between the DNA and the RNA. All right. So now between DNA and RNA, some of the differences that we know of. The first one, perhaps the most important one, is in the structure itself, where we say that one is deoxyribonucleic acid and one is called as ribonucleic acid. So what we see with deoxyribonucleic acid is that it's a double-stranded molecule, right? It's a double-stranded molecule, whereas in case of an RNA, it is a single-stranded molecule. So if you have to think of what the structure is like, think of DNA as having a ladder, that you have a ladder which you have twisted, right? So if you twist the ladder, the kind of structure that you get is basically the deoxyribonucleic acid or DNA. Whereas when it comes to ribonucleic acid, you just think of the same ladder which is twisted, but you have half of that ladder. That you, let's say you take the ladder, you cut it in one half, so you only have the half of the ladder, and then you twist it. So then the kind of structure that you get is called as is the structure of RNA. So if you see here, this is the structure of the DNA, where you have a kind of a twisted ladder. And let's say you only had the half of it, right? Let's say you only had the half of it, then it will be the RNA. So that's the basic difference between RNA, that you have a single strand and you have a double strand in DNA. The DNA is double stranded and RNA is single stranded. All right. So that's something that is basically the basic difference between it. Now, the second difference, as I told you, the location. The location, what we see is that in case of DNA, largely it will be found inside the nucleus of the cell, whereas when it comes to RNA basically will be found in the various different parts of the cell. All right. It will be found in various different parts of the cell. So that's the basic difference in the location. Also found inside the mitochondria. Right. Also found. We'll discuss about why inside mitochondria later, perhaps not today, but in tomorrow's class. But this is also what we see. Not only that, I mean, there is a question. Let me ask you a question that actually UPSC has asked once. They had given you three options, three parts of the cell: nucleus, mitochondria, this was a question, and plastids. Plastids which are found inside the plant cells. And they have asked which of the above have DNA. This was the question. Right? One only, one and two, one and three, all. This was the question asked. I'm giving you time, just mark your answers. This was asked in UPSC Prelims 2004. Has been a very long time, almost 20 years back, but a very interesting question. So 51% of you have marked D, which basically is there on the slide. 27% of you have marked D, which actually is the correct answer. The correct answer is B, all. In the plastids also we find DNA. So that's why DNA is not only found inside the nucleus, but it is also found inside the mitochondria. Yes, nucleus and mitochondria are common among the plant and the animal cells, whereas plastids are only found in the plant cells. Plastids are responsible for making chlorophylls which can help in photosynthesis. So plastids actually also contain the DNA. So that was the question asked. So anyway, coming back to the topic of discussion, what we are saying is that this is where there is a difference. Now, one more difference that we have is in the chemical bases that they have. In case of DNA, we discussed that they have adenine, guanine, thymine, and cytosine. Whereas in case of RNA, there is one difference, that you don't have thymine. Instead you have uracil, another kind of base that you have. So that's the basic difference. Others are the same. Only there is one difference in the chemical bases that we have. So, and in the function also, they of course are different, because they are related to the genetic information, and they will be required for any kind of characteristic that we have. And when it comes to RNA is required for protein production from the nucleus to the ribosome, and we see that RNA will be useful there. So in all these cases, we see that there are these differences. So this is something that can be important from the perspective of your prelims examination. So just understand the basics of what differences are, that what is a gene, what is a DNA, what is a chromosome. The basics should be clear. You should know that when to use what term, because very often you'll see that in this chapter, these terms will be used very casually, right? That what is a gene, what is a DNA, what is a chromosome. You should know the basics of what is right, what is wrong, and how exactly they are different. So we have DNA, which become the base of everything. From the DNA, set of DNA together will form genes, and all these will form into 23 pairs of chromosomes. So we have 23 pairs of chromosomes, we have more than 20,000 genes, and we have a lot more DNA. So that's why this is basically how we are looking at the differences between all these three terms. Now coming to biotechnology. So studying out biotechnology, what we are going to study are the various applications. This chapter is more about the applications of biotechnology in various different fields in whatever way we can, right? Whatever way we can. So when it comes to the branches of biotechnology, the first one is green biotechnology, where we are talking about agriculture. Anything related to agriculture is called as green biotechnology. Second branch is red biotechnology, which is related to medical science. Anything related to the health related applications, we call it as red biotechnology. Then after that, we have blue biotechnology. So blue biotechnology is the use of biotechnology underwater. Blue color generally is associated with water, so that's why blue biotechnology, any water related application. White biotechnology applied to industrial processes. Whenever we are using biotechnology for industries in one way or the other, it is called as white biotechnology. Similarly, we have gray biotechnology related to environmental applications. Wherever we are using it in cleaning the environment, in cleaning the pollution, we'll be calling it as grey biotechnology. Then we have red biotechnology related to the deserts. Anything related to, let's say, for example, growing crops in arid areas or with limited supply of water, we'll be calling it as brown biotechnology. Then we have violet biotechnology. So violet biotechnology is anything that is not a direct application of biotechnology. For example, laws related to biotechnology will be violet biotechnology. The schemes, policies, and the programs by the government on biotechnology will be called as violet biotechnology. Similarly, let's say intellectual property rights related to biotechnology will be called as violet biotechnology. So any philosophical issues, ethical issues, etc., being discussed, any laws, regulations being discussed, all will become violet biotechnology. And then lastly, we have dark biotechnology. So dark biotechnology is related to all the negative applications or the negative impact of biotechnology in one way or the other. So that will be called as dark biotechnology. So we'll be discussing all this. We'll be discussing all this one by one. This is basically what the chapter is about. That one by one, we'll pick up all these branches and we'll discuss about these branches. We'll try to understand these branches and how these branches are useful for us in today's world. Right. So first one to start with, these are medical applications, and as we call them as red biotechnology. Red biotechnology. So in red biotechnology, we see that there are a lot of applications, there are a lot of different ways in which we can make the use of biotechnology in the health sector. And today we have been doing that a lot. If you look at, for example, let's say if you take India's example, what you will find is out of all the money that we spend on biotechnology, majority of money is actually being spent on red biotechnology. Out of every 100 rupee that we spend on biotechnology, more than 70 rupees are spent on red biotechnology, and that too in a particular form of red biotechnology, that is biopharma. We'll discuss about what is biopharma. So in biopharma, we see that more than 70% of all the investment that happens in India, whether it's the government spending or it's a private institution or a bank spending, more than 70% of the spends they happen on biopharma. So that's why just understand the value of this red biotechnology. That amount of money being spent here is enormous compared to any other branch of biotechnology. The most amount of money is spent on the research related to red biotechnology. And why so? Very simple. Because we know that a lot of unsolvable issues of today will be solved with the help of biotechnology. We already have been doing that with the help of techniques like stem cell therapy. We'll discuss that later. So with the help of these kind of techniques or genetic engineering or gene therapy, etc., we have been able to solve some of the unsolvable problems of the day. And that is the reason why we are looking at all these applications. So first and foremost, gene therapy. What do we mean by gene therapy? What is the use of genes? We discussed that genes carry certain special properties, right? Certain special characteristics are there in the gene. So many times, there are diseases that might occur because of presence or absence of a certain gene, or maybe a defect in a certain gene. All right. So some diseases, or not some, let me write many diseases are associated with the presence, absence, or a defect. Presence, absence, or a defect in a certain gene. So this is basically where we will be trying to use gene therapy. What do we do in the gene therapy? We either, let's say if it is about because of presence of a certain gene, some problems are happening. What do we do with that gene? We remove that gene. Let's say some disease is happening because some diseases are occurring because there is an absence of a particular gene in your body. What do we do then? We add that gene. Right? Let's say something is happening because of a defect in a certain gene. What can we do? Either remove it or modify it. So either we will modify it so that we can correct the mistakes in the gene, or we can remove the gene. If it does not cause any harm, then we can simply remove that gene. So either it can be about removal of a gene, it can be about addition of a gene, or it could be about modification of a gene. So this is how we would carry on gene therapy. This is what we can do. So it can be about addition of a gene, it can be about addition of a gene, or removal of a gene, or it can be about modification in a gene. So in this manner, we see that we can carry on these processes, and these processes can be related to what is happening here. So if it is because of presence of a certain gene, then we would try to remove that gene, right? If it is because of absence of a certain gene, we would want the addition of this gene, correct? And if it is about a certain kind of defect in a gene, then either we would want to remove that gene or replace that gene, let's say. So removal, replacement, or modification. We would try to correct the mistakes. So in this manner, we will try to take care of the problem that has occurred. So many of the problems that we haven't been able to solve with the help of a medicine, with the help of vaccines, etc., all these kind of problems, they can be solved with the help of gene therapy. So hence, we see that today gene therapy has become very, very important. Then we have something called as genetic testing. Now, these genetic testing basically are testing for a certain gene, or maybe if there is certain mistake or certain changes that have happened in the gene. So either the presence or absence of a gene, or maybe the changes that have happened in the gene, so that we can detect a certain disease with regards to something similar. So what we see is that suspected genetic condition can be determined here, or it can also help us understand the chance of a person developing or passing on a genetic disorder. Not only that, there are certain diseases for which we can also test. For example, today if you see, there are a lot of lab tests which are very easily available for us. In a lot of cities in India, you would today see that you can call for a lab test, they can come to your home, collect the blood samples, etc., and they'll give you the report. Many of these, if you see closely, you'll find that they can also do a cancer detection test, they can do a diabetes detection test, and so on. How exactly can they do that? They will be looking for certain genetic markers. They will be looking for certain genetic markers. These are basically genes that can give you an early information about something that has started to develop. So even if, let's say, there are chances that a person might become diabetic in the next 10 years, you will see some of the early indications of that in the genes. So that is what they will be looking for. Same goes for cancer as well, that early detection of cancer can be also done genetically. So many times it's not only about the genetic disorders, but also we see that in these kind of genetic markers as well, we'll be able to detect certain diseases early. So that is why genetic testing also becomes useful. And then comes drug administration, where there is one very, very important term called as biopharmaceutics. Biopharmaceutics. So biopharmaceutics, again, just try to break down the words bio and pharmaceutics. What is pharmaceutics? Related to medicines, correct? What is then biopharmaceutics? So in case of biopharmaceutics, we basically are trying to understand that any medicine that we are using, what are the various properties of those medicines and what are the various effects of those medicines on the body. So, for example, how fast does the medicine work? How much time does it take? What is the rate of absorption? What is the rate of excretion? What are the physical and the chemical properties of the medicine that might have an impact on the body, positive or negative impact on the body? So, studying all those interrelationships, so the side effects, if there are any. So, when we study all these things, they all will be studied under biopharmaceutics. Right? They'll all be studied under biopharmaceutics. So, that's why pharmaceuticals basically are related to medicines. And when you are looking at their effects in one way or the other, they'll be called as biopharmaceutics. As I told you, more than, I'm just writing it out here, just a basic data, that more than 70%. More than 70% of all the money spent on biotechnology in India is related to biopharma or biopharmaceutics, right? So we know that it's very, very important because we are constantly trying to solve all the health issues that we have in the country. So that's why biopharmaceutics becomes a very, very important part. So it examines the interrelationships of the physical and the chemical properties of the drug, the dosage form, and the manner of drug administration on the rate and extent of drug absorption. So that's why each and everything related to the use of medicines in our body, the positive and the negative impact, the rate of absorption, and so on, all these things will be examined as a part of biopharmaceutics. So that's why biopharmaceutics becomes very, very special here. Then there are multiple different things which can be done as a part of biopharmaceutics. For example, there is a sub-branch called as pharmacokinetics. Now again, break down the words and you will kind of get the meaning. Pharmacokinetics, pharmakinetics. Pharma again related to medicines. What is kinetic? The word kinetic related to? What is the word kinetic related to? Can you tell me first? You might have heard of kinetic energy, for example. So what is that word kinetic related to? Yes, motion, movement, correct. So anything related to motion. When do we say kinetic energy? The energy due to motion is called as kinetic energy. Similarly, here also we are talking about pharmacokinetics, meaning that here we are talking about the movement of the drugs, movement of the medicines. So the rate of absorption of the medicines, how fast is it being absorbed by the body? How fast does it get excreted out of the body? How fast does it start to work inside the body? What are the things that we can do? What are the changes can we make so that we can make it faster, or we can work according to the disease? Because we know that every disease has its own pace. There are diseases that can start acting within a couple of hours, and there are diseases that can take more than 2 years. So all these diseases, they have their own pace. And how do you ensure that your pace or the pace of the medicine is faster than the pace of the disease? You have to ensure that if let's say there is a disease that takes its effect in 2 days, then you'll have to ensure that you are doing everything to ensure that that medicine can start working within a day, right? That medicine can start working within a day, correct? So that before the disease it can take its effect. So you will have to do that, correct? So that is what pharmacokinetics is all about. It's about the movement of the medicine. It's about the movement of the medicine in and out of the body and the rate of absorption. Then after that, we also have something called as pharmacogenomics, right? Again, two words, pharma and genomics. So when it comes to pharma, again, we are talking about medicines and genomics. Genomics is what? The study of genes. The study of genetics, the genes is called as genomics. So when we are looking at the interrelationships between the gene, the genetic makeup of an individual versus the medicine, then in that case, it will be called as pharmacogenomics. So that's why it is a combination of genetics and pharmaceuticals. So how genetic makeup affects an individual's response to drugs is what we study as a part of pharmacogenomics. And this pharmacogenomics also becomes very, very crucial, and it's a very, very important application of something called as DNA fingerprinting. DNA fingerprinting, something that we are going to discuss in tomorrow's class. DNA fingerprinting. So becomes a very, very crucial part of DNA fingerprinting. All right. So this is basically what we look at when it comes to medical applications. A couple of more. So for example, there is something called as virotherapy. So again, if you break down the word, it is virus plus therapy. So whenever you are using virus, whether to make an antiviral drug, whether to make a vaccine, in all these cases, wherever you are making the use of virus in one way or the other, it is called as virotherapy. Similarly, we have insulin. So you might know about insulin, that insulin is required by our body to maintain the sugar levels, so that excess sugar from the body can be thrown out, can be taken away, and that is where insulin works. So what we see in diabetic patients is that the making of insulin by the body reduces. Either the body is making very low amount of insulin or is not making insulin at all. So then in that case, you might see that the diabetic patients will take insulin injections so that insulin can be provided to them artificially, right? Externally, we can provide insulin because the body is not making enough of insulin now. So then excess sugar from the body cannot be removed. This is what happens in case of diabetes. So insulin also is a part of the biochemical process of the body. So that's why insulin being used is also, you can see in a manner, it is also an application of biotechnology. Apart from that, there are other such applications that we are going to discuss later. For example, we have stem cell therapy. We have some use of cloning as well. We are going to discuss DNA fingerprinting as well. So these are some of the things that we are going to discuss later. I mean, not today, we are going to discuss it tomorrow. But all these things, basically, they are also related to medical applications. And this can directly become a question for you in the mains examination. They can ask you, what do you mean by red biotechnology? How does it help? Or what are the health applications related to biotechnology? These can be very direct questions that they can ask in the paper. So all these specific terms and what exactly they mean, what are we doing, the developments that happen in India, any new policy, any new program, any new scheme, all those things become very, very crucial from the perspective of medical applications of biotechnology. Then we have the agricultural applications. Now, in case of agricultural applications, again, what we see is that after red biotechnology, if there is any branch of biotechnology which is very, very significant, it is agriculture. It is the green biotechnology. Right? This is green biotechnology. Now, when it comes to green biotechnology, the application is in agriculture. This crop that you see right here, this picture that you see right here, has been one of the most successful examples of biotechnology applications in agriculture. Anyone who can recognize this for me? Great, wonderful. So many of you know this, that this is what? This is a certain kind of cotton called as BT cotton. Right, certain kind of cotton called as BT cotton. So now this BT cotton became one of the most successful examples of biotechnology application in agriculture. The problem that we were facing with cotton cultivation was that a lot of cotton crops were getting destroyed by the action of a certain pest called as bollworm. right? Certain pest which is called as bollworm. And with bollworm, what we saw was that these bollworms, they would simply eat upon cotton crops and destroy cotton crops. So this was a big challenge. Almost there was, you can say, as high as 20 to 25% reduction in the productivity because of what we saw as the action of this particular pest, that is bollworm. What did we do next? We found a bacteria which is basically called as Bacillus thuringiensis, and this bacteria, or BT, this BT is a kind of a bacteria called as Bacillus thuringiensis. Now, this bacteria, once we found that this bacteria could actually provide a property to this cotton, where cotton will start becoming poisonous for bollworm. That this cotton will start producing its own pesticide, you can say, in a manner that it will be able to produce its own pesticide, where it will become poisonous for bollworm. So now what we did is that we found this property in this bacteria, and we inserted this bacteria inside cotton. And while we did that, this bacteria, because of this presence of this bacteria, we see that now this cotton becomes poisonous. This cotton becomes poisonous for any bollworm, and hence we were able to increase our productivity. So this has been one of the most successful examples of the use of biotechnology in agriculture. So when it comes to agriculture, what we produce is something called as a transgenic plant or a transgenic crop. Now again, try to understand the meaning of the word itself, that is transgenic. What is transgenic? So again, if we try to break down the word, you have trans and genic. Where do you use the word trans? Think of the word transfer. What do you mean by transfer? Transfer means that somebody is going from one place to another. That is what you mean by transfer. So anything where something is, let's say, moving from one place to another, or let's say there is something that is coming from somewhere else, you'll use the word trans. So transgenic is when we are saying that the genes are coming from somewhere else. So what we saw in cotton, in BT cotton, that we took the gene from the bacteria and we put it inside cotton. So when you take the gene from another organism, any organism, it could be another plant, it could be another animal, it could be a microorganism, it could be a human, it could be an alien species, you don't know, right? Just depends on the property that you need, right? So for example, let's say you want your plant to move, you want your trees to move, as Lord of the Rings has shown, or as Marvel movies have shown in terms of Groot, where you know that there is a walking and talking plant or a tree which says I am Groot, or talking trees that we had in Lord of the Rings. So in all these cases, if you want to produce something like that, the only thing that you need is that you have to find that gene that helps us move. You take that gene, insert it inside the plant, inside the tree, and the tree will start moving. Unfortunately, things are not that simple. Otherwise, we would have had a lot of moving trees all across. But things are not that simple, and we'll discuss about the complexities later. But when we say transgenic, this is the meaning of the word trans. All right. So that's why transgenic means that the genes are coming from beyond. It is coming from somewhere else. So that's why we are using the word transgenic. Just remember, it can come from any organism. It can come from any organism. Just that it should be able to work along with this plant. It should not. Many times it will not work. But if it works, you will be able to add that property. So that is why it can come from any other organism. So another unrelated plant or from a completely different species altogether. So then in that case, it is called as a transgenic plant. Now, these transgenic plants, many times they are also called as genetically modified organisms or genetically modified crops. So we call them as genetically modified organisms, or in this particular term, crops. So the term GMO is used many times, or GMC sometimes is used. So these basically are the transgenic crops for us. Okay? These are the transgenic crops for us. So this is basically what we would observe in terms of the transgenic plants or the crops. So overall, this is what we see. This is what we would observe in transgenic plants or transgenic crops. Now there are various ways that if I ask you a question, why would we produce transgenic plants? So either it could be about productivity, as we have discussed in the case of BT cotton, that it has been about productivity, increasing the productivity of the crop. Or it could be about increasing the nutritional value. It could be about the nutritional value. For example, let's say you want to add certain nutrients to a certain kind of a crop. Then in that case, you can do that. We can do that. And in that case, we'll be able to increase the nutritional value. One basic example, simple example has been the case of golden rice. All right, in case of golden rice. So if you see, this is the normal rice, the white colored rice. This is the normal rice. And this is the golden rice. So this yellow colored rice is also called as golden rice, because why would you call it as yellow rice? Doesn't look good. When you call it as golden rice, we think that it is something premium, something important. So that's why golden rice. So this yellow colored rice, or let's say golden colored rice, is called as golden rice. Now you can see there is a difference in the color. The difference that comes in the color is mainly because of certain genes that we add, and these genes, once added, they will basically have beta carotene, and this beta carotene converts into vitamin A. So because it converts into vitamin A, what we see next is that this golden rice will have vitamin A. Now generally you don't consume rice for vitamins, right? Rice is a source of what nutrient? Which nutrient does your rice have? Yes, it has the carbs, or as we call as carbohydrates, right? So it has the carbohydrates, it gives you energy. So it doesn't have vitamins. But when we add these genes in rice, it will start having vitamin A as well. So in case of golden rice, we are adding nutritional value to rice. Why would we do that? In certain areas, we see that there might be either deficiency in people, they might not have enough of vitamin A. So then in that case, these kind of crops can become useful. These kind of crops can become useful, and they can be then used. They can be then used for this purpose. So that's why we see this can be done. Increasing the shelf life is also possible. Right? We can increase the shelf life, and there are environmental benefits as well. That shelf life also through the genes, adding certain genes can improve the shelf life, and then there can be environmental benefits as well. So environmental benefits largely will be from the perspective of that, let's say something like BT cotton. So in case of BT cotton, because the cotton crop itself is producing its own pesticide, you do not need chemical pesticides to be added to them, right? We don't need to add chemical pesticides to them. They can produce their own pesticides, and hence that will work for them, right? So that's why it will have environmental benefits as well. So there are multiple such reasons why we would do such a modification, and it's different from traditional plant breeding practices, because in traditional plant breeding practices it's more of a hit and try method, that we did something, it worked for us, we kept doing it, or something happened by chance, and because of the advantages that we saw in that problem, that thing that happened, we keep continuing it later. So many times we may not see a positive result in a long term basis. It might show some positive results sometimes, may not show those positive results at other times. So that's why there is no guarantee, right? There's no guarantee to whether it will work or not, whether it always works or not. So that's why we see that in terms of traditional plant breeding practices, these are more of hit and trial methods, where we have tried something, sometimes it works, sometimes it did not. But in case of use of biotechnology in producing the transgenic plants, we see that whatever we are doing is for a reason. That we found certain genes, we tried those genes, they work, and hence we kept on using it. So that's why we see that in case of the transgenic plants, we are using modern biotechnology, whereas in case of traditional plant breeding practices, we are not using modern biotechnology. It can be just about artificially crossing the plants with the same species or any closely related species, and we try to see what happens next. So that is where we see that these are different. So there are how the development of transgenic plants happen. We will probably discuss it in tomorrow's class because it takes some time for me to discuss and we don't have enough time. Let's end with this question. Look at this question. Read this question and then I'll also launch the poll for you. I'll give you a minute. Please mark your answers. Right. So out of all the answers marked, 15% of you are marked A, 6% B, 36% C, and 43% D. So the question is talking about recombinant DNA technology that we are going to discuss later. Don't worry, tomorrow we'll discuss this. Allows the genes to be transferred. So where the genes can be transferred from and to, we have discussed this. Across different species of plants. Possible? Yes, possible. We have done that in case of golden rice. The beta carotene that synthesizes vitamin A comes from daffodil plant. So across various species of plants, yes, possible. Because it talks about allows the genes to be transferred. Right? Where is it allowed from? So across different species of plants, yes, possible. From animals to plants, yes, possible. Just remember, this is what we discussed, and I was emphasizing so much on it that you can take it from any organism. Theoretically, you can take it from any organism that you want. You take it from a plant, you take it from a microorganism, you take it from an animal, you take it from human. You call upon Jadoo and alien and take the genes from there if you want. Take it from anywhere you want. So that's why there is no restriction of where you can take it from and where you can't take it from. So that's why even from animals to plants, it can be done. Yes, it's very, very difficult to do it. It's almost impossible to do it because animal genes are very different in their nature from the plant genes and the structure is very different. But we do share genes. I mean, for example, between humans and even banana. Do you know the amount of similarity that we have between our genes and the banana genes? Do you know that? So almost 60%. Right? The answer is around 60%. Yes, Pratham, you have given the correct answer. That around 60% of the genes between humans and bananas are shared. So why is not the transfer possible? Yes, it is. So that's why from animals to plants also possible, although very, very difficult. From microorganisms to higher organisms. Yes, present in case of BT cotton, that is what we are doing. So that's why microorganisms to higher organisms is also possible. So all the three are correct. All the three. So that's why remember any organism. You can take it from any organism that you want. Anyway, so let's end the session here. If you have any questions, please let me know. Let's have a discussion on all the questions and then we shall end the session for today. What is the reason behind the change of color normal to golden rice? The reason is the beta carotene that we have taken from daffodil. That is yellow in color and hence it imparts its yellow color to rice. BT bacteria was introduced on cotton or its genes, the specific genes, the genes that were related to those properties, those genes were introduced. CRISPR-Cas9 will have a discussion when we discuss about the recombinant DNA technology tomorrow. So there I'll discuss it. Leaderboard. Let me show you the leaderboard. Yeah, this is the leaderboard for today. Three parents baby will discuss tomorrow. Briefly explain chromosomes. So chromosomes basically you can say they are thread-like structures that we have inside the nucleus, and these chromosomes are made of DNA. So the entire DNA structure that we have, they are first of all they are categorized in various genes, and all these together they make up the chromosome. Right? All these together they will make up the chromosome, and hence this is how we look at them. Right? This is how we look at what exactly happens. So there are 23 pairs inside humans. Every organism will have their own set of chromosomes, and they are related to all the genes that you have. All these genes will basically make up these 23 pairs. Right? So I hope you've seen the leaderboard. All the rank ones. I'll send my address. Please send me the gift. Limited risk of proliferation of nuclear fusion, please explain. So proliferation is, the meaning of proliferation is nothing but weaponization. So we are saying that risk of weaponization here directly from this process is very difficult. The process of making a fusion based bomb or a hydrogen bomb is very different. So you cannot use your nuclear facilities for that. Whereas in case of nuclear fission, we can do that. We have been doing that. India has been doing that. Other countries have been doing that. So that is where we know that it can be weaponized easily, whereas it can't be weaponized easily in case of fusion. We'll remove the genes from human body by transferring the genes of banana. We won't do that because it's a very difficult process to carry on anyway. But yes, I'm just giving an example that there are so many shared genes among various species of even plants and animals. Can we leave now? Yes, you can. I mean, if you don't have any further questions, you can. How India disposes its vestige, nuclear vestige? Same. I mean, what we discussed, there are certain nuclear facilities, well-guarded nuclear facilities that we have in India, and all those nuclear waste, they will basically go there, and depending on what kind of waste it is, it will be segregated and it will be accordingly disposed of. Can golden rice be called as a GM crop? You can say that, yes. What are Trojan asteroids? So Trojan asteroids are the asteroids which are often found in the Lagrange points of any given planet. So whether on L4, generally on L4 and L5, L1, L2, and L3 are very unstable points, so it's not easy for Trojans to just come there and live there. But L4 and L5 are stable points. So sometimes what happens is that the asteroids get stuck at L4 or L5 of a planet. In that case, they're called as Trojan asteroids. What did you explain about the combination of sugar in DNA? Sugar in DNA, I did not explain anything about that. I'm not sure. What is BT cotton? BT cotton, as I told you, that BT cotton is nothing but a cotton variety where we have added genes from a bacteria so that cotton can make its own pesticide and it can become poisonous for bollworm and thus improve the productivity. Any examples of genetically modified crops that are tolerant to certain adverse climate conditions like droughts? Yes, we do that. We do that all the time in many of the crops, where many of, for example, even in rice, we have been trying that not for drought conditions, but even so that we can decrease the consumption of water. Similarly, in other crops that grow in less rainfall areas, there also we have been doing that for a long time now. Issues related to books, I'm not sure about it. If you can talk to the support team, they can probably help you. Why there is so much discussion on Dhara mustard? Dhara mustard. So Dhara mustard we'll discuss tomorrow. DMH11 we'll have a discussion tomorrow. Don't worry. How is it possible to transfer the genes of plants to animal? We'll discuss. We'll discuss that. Where heavy water has been used? Heavy water is used in nuclear facilities and nuclear reactors. We use it. How control rods absorb extra neutrons? Because control rods are made of metals, so metals in general they have the capacity to absorb extra neutrons. So this is what we see, especially with the lower metals, it's possible. So boron and cadmium, these kind of metals can be used. Especially the group 1 and group 2 elements, they have a better capacity to do that. Why same fruit or vegetables like onion differ in physical characteristics in one or other country? It is due to genes. Yes, it is due to genes. There are genetic diversity that will be produced all the time. I mean, from one generation to another, there can be certain similar differences that can crop up in the genes, and that will lead to those genetic modifications. So that's why it happens. In Chernobyl, what kind of reactors were used? The same pressurized heavy water reactor is used in Chernobyl as well. Also, Pakistan and countries that bought nuclear tech from it, like North Korea, Iran, use some kind of sheet method to produce bombs. How is it different from the tech used by India? So basically, what happens here is that in case of, I mean, when you try to increase the enrichment, when you try to increase the enrichment, that is where these kind of technologies can be used. And it's not that India can't. India has the technology, but we haven't been using it. We have made it very clear to the world that we'll be using nuclear technology for peaceful purposes. We'll not be using it for anything else. But yes, through the testing, we also have shown that we have the methods ready where we can use it. So now the method that you're talking about, especially what happens is that it increases the time frame. I mean, decreases the time frame in which the enrichment can be done, and it helps them enrich in a kind of an unsafe manner. Enrichment can be done faster. So that is basically what happens there. The enrichment levels there, for example, can go to as high as almost up to 85%. Yes, we have the no first use policy. That's correct. All right. So I think I've taken most of the questions that were here. About the books, I'm not, even if there is any problem that you're facing, please, or if you can write, you drop an email to me also, I'll check with them if there is anything that can be done. The main questions we'll discuss tomorrow. Some of the main questions we'll discuss tomorrow. All right. So this is it for the session. Please go back, revise the things, whatever we discussed here. If you have any doubts, please bring them back tomorrow. We shall continue with our discussion on biotechnology. We'll complete the chapter of biotechnology tomorrow, and the next chapter that we have is nanotechnology. So that's what we are going to discuss in tomorrow's class. Thank you.